Hello, and welcome to the Snoozy Scientist. I'm really glad you made it here tonight. Wherever you are on this planet, this quiet space was made just for you, a small pocket of calm where science and curiosity can meet to guide you toward rest. Tonight, we're going to explore one of the strangest, most improbable stories Earth has ever written. A story so unlikely that by all logic, it should never have happened at all. They call Earth the blue planet, a world wrapped in oceans, crowned with clouds, and alive with rivers that never rest. But beneath that peaceful surface lies a truth far more unsettling. By everything we know about how planets form, Earth was never supposed to look like this. When our world was born 4.5 billion years ago, it wasn't the lush ocean-covered sphere we know today. It was a raging fire, a ball of molten rock and metal, its skies filled with choking gas and burning ash. The young sun's heat was so intense that any water should have boiled into space before it could ever gather. The surface was too hot, the air too thin. By every calculation, Earth should have been a dry, lifeless stone drifting around the sun. And yet, it isn't. Somehow, this planet defied the odds. Oceans appeared where none should have formed. Today, more than 70% of its surface is covered in water, the one substance that every living thing depends on. But here's the part most of us never think about. Water isn't truly Earth's own. It didn't simply appear as rain or bubble up from the ground. It had to arrive here, piece by piece, drop by drop, carried from beyond. And in all our searching across thousands of planets and distant star systems, scientists have yet to find another world with liquid water flowing openly across its surface the way it does here. So where did it come from? What chain of cosmic accidents turned a burning rock into the blue marble we now call home? Tonight, we'll trace that story from the birth of the first atoms in ancient stars to the day the first rains fell on a silent world. And along the way, we'll discover how water didn't just shape Earth, it made Earth possible. If you're already settling into this calm space, it would mean a lot if you gave this video a gentle like and maybe subscribed if you'd like more quiet journeys like this. And if you feel comfortable sharing, I'd love to know, where are you listening from tonight and what time is it there? It's always a joy to see how far these stories travel. So now, take a deep, slow breath, and together, let's begin our journey into one of Earth's most beautiful mysteries, the story of how a world that should have been dry became the planet of water. In the vastness of our solar system, there is a quiet rule that seems to govern the way planets are born. It is written not in words, but in temperature, distance, and chemistry. It is called the frost line. This invisible boundary, lying far beyond Earth's orbit, is where the newborn sun's warmth fades enough for water vapor to condense into ice. Inside that line, where Earth, Venus, and Mercury circle the sun, the heat is simply too intense. Any water that tried to form would be vaporized and driven away before it could ever settle. By all logic, planets born inside this dry inner zone should be scorched, airless, and barren, and for the most part, that rule holds true. The two closest worlds to the Sun, Mercury and Venus, are perfect examples of how the frost line shapes planetary destiny. Mercury is a tiny baked world, its surface blasted by radiation and stripped of almost all atmosphere. Any water that might once have existed there vanished billions of years ago. Venus, slightly farther out, is larger and wrapped in a thick atmosphere, yet its surface is an inferno. The intense heat has boiled away whatever water it once had, leaving only a suffocating haze of carbon dioxide and sulfuric acid. By the laws of planetary formation, Earth should have shared their fate. It was born in the same dry neighborhood, forged from the same rocky debris, shaped by the same blazing light of the young sun. And yet it did not become a second Venus or another Mercury. it became something entirely different, a world where rivers carve valleys, where rain feeds forests, and where great oceans stretch endlessly beneath drifting clouds. This contradiction is one of the most profound puzzles in planetary science. The frost line tells us that water should never have condensed so close to the sun, yet Earth is overflowing with it. More than 70% of our planet's surface is liquid water. Vapor fills the air, ice blankets the poles. Every living thing on the planet depends on it. Our entire biosphere, from the deepest trench to the highest mountain peak, is shaped by the presence of water. Scientists have spent decades trying to understand how this is possible. They have studied meteorites and planetary dust, traced the isotopic signatures of water, and built models of how planets grow. Yet the mystery remains unsolved. The simplest explanation would be that Earth formed farther from the Sun, beyond the frost line, and later migrated inward. But the evidence does not support that idea. All signs point to Earth forming where it is now, in the dry inner solar system where water should not exist. The frost line itself is not a hard wall, but a gradient, a region where temperature shifts from hot to cold, from water's gaseous form to its icy one. Beyond that line, in the cold outer reaches, ices can clump together and become part of the building blocks of planets. Inside it, water remains a gas and is easily swept away by solar winds. That is why the outer planets, like Jupiter and Saturn, have moons made of ice, and why comets born in those distant regions carry frozen water deep within them. Earth, however, sits well inside this boundary. According to the rules of planetary chemistry, its original materials should have been bone dry. Mercury and Venus stand as reminders of what should have happened here. Mercury, too small to hold on to an atmosphere, became a sun-scorched wasteland. Venus, with its thick clouds, once might have had shallow seas, but rising temperatures sent that water to the skies, where ultraviolet light split the molecules apart, and solar winds blew the hydrogen into space. Their desiccated landscapes are the expected outcome of forming within the frost line. Earth's water-rich environment is not. Some scientists suspect that the reason lies not in where Earth formed, but in what it was made from. Perhaps the rocky material that built our planet contained trace amounts of water trapped within minerals delivered during its chaotic formation. Others propose that water came later, carried in by icy asteroids flung inward from beyond the frost line. Or maybe both are true, and Earth's water is the result of multiple overlapping processes, each leaving its signature on the oceans we see today. Whatever the explanation, one fact is certain: Earth is a cosmic exception. Among the inner planets, it alone defied the rule of the frost line. It alone transformed from a place that should have been dry into a planet defined by water. This paradox is more than a scientific curiosity. It is a reminder of how delicate and improbable our world truly is, how a simple shift in temperature, distance, or composition could have erased everything we know. It is this very contradiction, this breaking of the rules, that makes Earth's story so compelling. It is not just a tale of water and rock, but of improbable chance. And in that chance lies the difference between a barren stone orbiting a star and a world that would one day cradle life. 4.5 billion years ago, the place that would become Earth was a furnace in the dark. Not a blue world, not a haven for clouds or seas, but a glowing sphere in a crowded nursery of forming worlds. Pebbles struck pebbles, stones struck boulders, and growing bodies collided with the force of suns. Gravity pulled the fragments together, and the energy of each impact turned rock to liquid. The young planet swelled larger with every blow and shone with a dull red light. Its surface a restless ocean of molten stone. Heat came from every direction. From above, incoming bodies slammed into the surface and released their speed as fire. From within, Freshly made minerals contained radioactive elements that gave off heat as they decayed. The result was a world so hot that any crust that tried to form was quickly broken and remelted. Imagine a skin on a pot that keeps forming and tearing, never long enough to cool or settle. In places, the molten layer may have reached hundreds of kilometers deep, rising and overturning like slow waves. The planet breathed in lava, not air. Overhead, the sky was a veil of gases rising from that liquid rock. Volcanoes were everywhere, sometimes entire ranges of them, pouring out carbon dioxide, sulfur compounds, methane, and thick veils of steam. Lightning forked through the haze, and ash drifted down like warm snow. These were not the clean skies of later ages. They were heavy and sour, shaped by chemistry at extreme temperatures. Water existed in that air as vapor, but the ground below glowed too hot for it to rest. Molecules were jostled apart by heat and by hard light from the young sun. They rose and dispersed into the higher atmosphere, where reactions carved them into fragments. Space itself was dangerous. Around the sun, other new worlds wandered on, changing paths. Some were cratered lumps only a few kilometers across. Others were full-grown protoplanets hundreds of kilometers wide. Their orbits crossed and tangled, and when they met, they did not pass gently. Earth took blow after blow, and each strike shook the planet to its core. The surface heaved, plumes of liquid rock blasted upward and fell back in incandescent sheets. The largest collisions did more than scar the crust. They stirred the deep interior and remixed the planet from center to surface. One impact was greater than almost all the rest. A body roughly the size of Mars struck the young Earth off center and at speed. Rock and metal splashed into orbit, and a bright ring formed in the wake. Over time, that ring gathered itself into a companion, our moon. The evidence for this colossal meeting lives in the chemistry of lunar rocks, and in the way the moon's makeup resembles Earth's mantle. The moon did not drift in from elsewhere. It was born from Earth's own torn skin. While the surface blazed, the inside of the planet was sorting itself out. Heavy elements sank. Iron and nickel moved inward like rain through honey, gathering into a core that still turns today. Around that metal heart, the mantle settled as a vast layer of dense silicate rock. Above it, the first fragile crust thickened in patches, whenever the surface had a rare, quiet moment. These layers were not fixed. Heat kept moving upward, and impacts kept stirring them. Even so, the broad pattern we know now began to emerge. A layered planet with a hot core, a plastic mantle, and a brittle outer shell that cracked and healed again and again. Every eruption changed the air. With each flare of magma, gases bubbled free from the deep and joined the growing atmosphere. Carbon dioxide became a major player. Sulfur gases added bite and color. Steam swelled the sky. The balance of all of these varied from place to place and from year to year, but the trend was constant. The air grew thicker, and that thickness held in heat. Even without sunlight, the planet would have stayed hot. With sunlight, it glowed. Nothing on the surface lasted long. Lava lakes formed, skinned over, and broke. Rivers of fire flowed downhill where gravity could grab them, carving temporary channels that froze into black rope and glass. New eruptions smothered the old. Mountains rose out of the liquid and melted back into it. The crust tried to knit itself into plates and then failed as the next wave of heat welled up from below. If you could stand on a rare solid island, the ground would tremble under your feet from the constant motion, and the horizon would flicker with red light. All this activity did more than sculpt the surface. It set up the chemistry that later ages would inherit. Volcanic gases reacted in the upper air. Minerals crystallized out of cooling rock and locked away elements in different combinations. The mantle learned where to flow and where to stall. The core began to spin in ways that would later produce a magnetic field. Even at this early date, the slow machinery of a complex planet was assembling piece by piece. Nothing about it was gentle, but everything about it was purposeful in its own blind way. The neighborhood calmed only by degrees. As the number of big stray bodies dwindled, the largest collisions became less common. The intervals between global catastrophes lengthened. The crust had more time to thicken before it was torn. Some of the volcanic arcs settled into long ridges that bled heat rather than spraying it. The atmosphere, though still harsh, was no longer being remade every moment. In the glow of that harsh stability, changes invisible to the eye began to matter more than the spectacular. Minerals in the shallow subsurface started to hold on to volatile elements. Basins that had been nothing but dents and lava hardened into true depressions that one day could be filled. Through it all, what we would someday call water remained a presence more in the air and in the rock than on the ground. The planet was teaching itself how to separate vapor from stone and how to bring heat from the deep to the surface in steady ways rather than in great bursts. Those lessons took time measured in millions of years. Until they were learned, the red world kept breathing in fire and breathing out steam. The surface heaved and glowed, but the skies had not yet learned how to make rain, yet the rocks would soon whisper a different memory. 4 billion years ago, the planet was still young. Its surface glowed with the fading heat of its violent birth, and the skies churned with steam and toxic gases. For a long time, scientists believed they understood what happened next. The sequence seemed straightforward. The surface would cool, volcanic steam would condense into rain, and water would slowly collect into oceans. According to this view, hundreds of millions of years would pass before the first waves lapped against any shore. But as researchers dug deeper into the story, Earth itself revealed a secret that upended that timeline. It was not a discovery carved into mountains or etched into layers of sediment, but something far smaller, microscopic crystals of a mineral called zircon. These tiny fragments, some no larger than a grain of sand, are among the oldest materials ever found on Earth. They formed in the earliest crust, surviving cataclysms that erased nearly everything else from that time, and within them lies a chemical memory of conditions long vanished from the surface. The oldest zircons come from the Jack Hills of Western Australia. They date back more than 4 billion years, a mere 200 million years after Earth first coalesced from dust and fire. At first, their age alone was astonishing, but when scientists examined the oxygen isotopes locked inside, the results were even more extraordinary. These isotopes revealed that the rocks had interacted with liquid water, not steam or vapor, but water in its flowing, pooling form. The implications were staggering. If the zircons were telling the truth, then water existed on Earth when the planet should still have been an inferno. Standard models of planetary evolution predicted a world too hot for rain, too unstable for rivers, too chaotic for oceans. The surface should have boiled away any moisture before it could gather. Yet the isotopic evidence left little room for doubt. Liquid water was present, touching rock, dissolving minerals, and shaping the chemistry of Earth's surface far earlier than anyone thought possible. This finding did more than shift a few numbers on a timeline. It overturned a fundamental assumption about how planets evolve. If water was already flowing so soon after Earth's formation, then something about the planet's early environment must have been very different from what scientists had imagined. Perhaps the surface cooled more quickly than expected, radiating heat into space faster than models predicted. Or maybe water was delivered earlier, bound up within the materials that built the planet itself, and released as the surface solidified. Both explanations challenged the traditional picture of a molten, lifeless world that stayed hostile for hundreds of millions of years. The evidence also suggests that a stable crust, one capable of supporting liquid water, formed surprisingly quickly. That in itself was a shock. Many researchers once believed Earth remained a global sea of magma for hundreds of millions of years, the crust repeatedly destroyed by impacts and internal heat. Yet the zircons indicate that solid ground was already present, exposed at the surface and in contact with water. This implies a planet that stabilized faster, cooled more efficiently, and reached a state suitable for surface water much earlier than once believed. The presence of liquid water so early also hints at something even more remarkable, a functioning hydrological cycle in Earth's infancy. If water was interacting with rock, then rain must have fallen from clouds. If rain fell, then evaporation must have lifted moisture back into the air. It suggests a planet that was not just cooling, but already experiencing weather, perhaps clouds forming and dispersing, storms sweeping across the surface, and water cycling between sky and ground, while asteroid impacts still rained from above. Yet, even as these ancient zircons reveal astonishing truths, they also deepen the mystery. They tell us water was here, but not how it got here or why it persisted. Did it arrive during Earth's assembly, delivered by hydrated minerals locked inside the planetesimals that built the world? Was it carried by early collisions with water rich bodies from the outer solar system? Or did it rise from the interior, forged deep within the mantle, and released as steam through volcanic eruptions? The zircons do not answer these questions. They simply state, in their chemical language, that water was present when it should not have been. This contradiction lies at the heart of one of planetary science's greatest puzzles. If water was here this early, then the traditional timeline from molten chaos to cool stability may be incomplete. Perhaps Earth's evolution was not a neat sequence of stages, but a complex interplay of delivery, retention, and recycling happening far earlier and faster than expected. Or perhaps there are still hidden processes we have yet to uncover, ones that shaped the planet in ways science has not yet imagined. What is certain is that these zircon crystals preserve the oldest direct evidence of water's presence on Earth. They are fragments of a forgotten world, a record of a time when the surface was young and the rules of planetary formation seemed different. They remind us that the story of Earth's water did not begin after the chaos ended. It began while the chaos was still unfolding. We will return to what this timing means when the rest of the story is on the table. One way to explain water this early is to look outward. In the violent infancy of the solar system, Earth was still an unfinished world. Its crust was thin and unstable, reshaped again and again by relentless impacts and volcanic eruptions. The air above it was a toxic haze, thick with carbon dioxide, methane, and sulfur, and the ground below still pulsed with the fading heat of its formation. If water was ever going to settle on this turbulent planet, it would need to come from beyond. Far from the newborn sun, beyond the orbit of Jupiter, a different kind of world was taking shape. Here, in the deep cold of the outer solar system, water could exist as ice. Countless rocky bodies formed with vast stores of frozen water locked inside them, trapped within minerals, or sealed beneath their surfaces. These were not delicate flakes of dust, but planetesimals, some no larger than mountains, others the size of small worlds. As the gravitational pull of the growing planets stirred the solar system into chaos, many of these icy wanderers were flung inward, their paths intersecting with Earth's orbit. What followed was an era of violence that lasted tens of millions of years. One after another, water-rich asteroids and protoplanets crashed into the young Earth. Each impact unleashed unimaginable energy, vaporizing rock, shattering crust, and sending molten seas of lava surging across the surface. Some collisions were so powerful they melted entire regions of the planet, briefly resetting Earth's surface to the fiery chaos of its birth. But along with devastation, they brought something far more precious: water, hidden deep within their rocky cores or bound inside minerals. That water was released the moment they struck. Some of it evaporated instantly, rising into the choking atmosphere and forming steam that would later condense as rain. Some was trapped again in minerals, buried deep beneath the surface until volcanic eruptions freed it millions of years later, and some stayed bound to the surface itself, accumulating drop by drop, collision by collision. Over countless impacts, the amount of water grew. Each asteroid was a delivery, each impact a shipment. And over time, the total delivery was staggering, enough, scientists believe, to fill Earth's oceans many times over. This process is known as late accretion, a crucial phase of planetary formation that followed Earth's initial birth. During this period, the solar system resembled a cosmic shooting gallery, with planetesimals and protoplanets careening inward from the outer regions. Computer models show that these bodies, formed beyond Jupiter where water ice was abundant, could have supplied an enormous reservoir of water to the inner planets. For Earth, this was not a gentle gift. These were not light particles of dust drifting down through the atmosphere, but cataclysmic blows from massive water-bearing bodies. The scars of this bombardment are still visible across the solar system, etched into the moon's surface, carved into the highlands of Mars, and buried beneath Earth's oceans and continents. The timing of this bombardment introduces one of the most fascinating puzzles in planetary science. Evidence suggests that liquid water existed on Earth astonishingly early, possibly within the first 200 million years of its history. Yet the period known as the Late Heavy Bombardment, when impacts peaked, continued well beyond that. If much of our water came from space, how could it already have been present before this wave of collisions had finished? One possibility is that water-rich asteroids began striking Earth earlier than once believed, even before the planet was fully formed. Some scientists think smaller planetesimals delivered significant amounts of water while the crust was still taking shape, long before the bombardment reached its peak. Another idea is that Earth's earliest building blocks already contained water from the start, and the later impacts simply added to that original supply. The two possibilities are not mutually exclusive. Water may have arrived in multiple stages, first during Earth's formation and again during the heavy bombardment that followed. Each colossal impact did more than deliver water. It reshaped the planet's surface, created basins where water could collect, and stirred the chemistry of the crust. Shock waves fractured rock, creating networks of cracks where water could seep and pool. The combined effects of heat, pressure, and volatile release transformed Earth's surface from a barren wasteland into a landscape ready to host oceans. Over millions of years, the interplay of violence and delivery brought the conditions for a hydrological system into place. These impacts were part of a larger cosmic story, one that continues even today. The water still falling to Earth from tiny micrometeorites, a gentle cosmic drizzle that accumulates over geological time, is part of the same grand process. But there is an important difference. The collisions that shaped Earth's youth were not soft or slow. They were catastrophic events, world-shaping blows that delivered oceans in violent bursts rather than delicate drops. They transformed the very nature of the planet, pushing it closer to the blue world it would one day become. By the time this great cosmic assault subsided, Earth was no longer the same planet it had been. Its crust bore the marks of its violent past, its atmosphere was thick with water vapor, and its surface was seeded with the ingredients for oceans. The stage was set for the next mystery and the next test. That elegant picture of water delivery from space would soon face new scrutiny, as scientists began to study the water itself in more detail. Its atomic signature would reveal a deeper story, one that would challenge even this grand explanation. In the early days of planetary science, the mystery of Earth's water seemed to have an answer that was both simple and beautiful. If our planet had formed too close to the sun for water to condense, and if its young surface was far too hot for any liquid to remain, then the oceans that now define our world must have come from somewhere else. For decades, the leading theory pointed to comets. These icy nomads, born in the frozen outskirts of the solar system, appeared to be the perfect couriers of water. They carried vast reserves of ice, and if enough of them collided with the forming Earth, their frozen cargo could have melted into oceans. It was a story that made intuitive sense. Comets, with their glowing tails and elliptical orbits, seemed like natural bringers of life's essential ingredient. They were ancient and water-rich, and their origin in the frigid realms beyond Neptune made them ideal candidates for transporting water into the warmer, drier inner solar system. For a long time, this explanation was accepted as fact, but science advances not only by asking questions, but by testing the stories we tell against the evidence. And when the tools finally became precise enough to examine water in fine detail, this elegant comet theory began to unravel. The key lay in water's chemical fingerprint, hidden within the hydrogen atoms that make up every drop. Most hydrogen atoms are simple, containing only a single proton, but a tiny fraction are heavier, containing an extra neutron. This heavier version is called deuterium. The ratio of deuterium to regular hydrogen, known as the D to H ratio, varies depending on where water formed in the solar system. It is like a signature, a unique marker of origin. If comets were truly the source of Earth's oceans, their D to H ratios should match the water we find on our planet. When scientists began measuring cometary water directly, however, the results were startling. Most comets, particularly those from the distant Oort cloud, had water that was far heavier than Earth's. Their D2H ratios were significantly higher, meaning their water had a very different chemical history from the water that fills our rivers and seas. This discovery struck at the heart of the long-held comet theory. If the water in comets did not match the water in Earth's oceans, then they could not have been the main source of it. At most, they might have contributed a small fraction. A few comets, especially those belonging to the Jupiter family group that orbit closer to the Sun, showed D to H ratios that came closer to Earth's. But even these were not a perfect match, and they were too rare to account for the planet's vast water supply. With comets no longer fitting the evidence, attention turned to a different type of cosmic body, carbonaceous chondrites. These are ancient meteorites that formed in the outer regions of the asteroid belt, much closer to the Sun than comets. At first, they seemed unlikely candidates. They were rocky, not icy, and they lacked the dramatic flare of comets streaking through the night sky. But when scientists analyzed their water, something remarkable happened. The D to H ratio of water locked inside these meteorites was nearly identical to that of Earth's oceans. It was the closest match yet discovered. This subtle but crucial detail shifted the focus of planetary science. The main source of Earth's water was likely not the icy messengers from the outer solar system, but primitive asteroids from the asteroid belt bodies that were far more common and much more likely to collide with the forming Earth during its violent youth. This pivot from comets to carbonaceous chondrites reshaped how scientists think about water's journey to our planet. It suggests that water was not delivered in one dramatic episode, but rather in countless collisions with rocky bodies rich in hydrated minerals. These minerals, heated during impact, release their water into the atmosphere and surface, gradually building the oceans over time. Instead of imagining water arriving as vast frozen blocks from the edges of the solar system, scientists now picture it locked within rock, delivered by asteroids that were themselves part of the same building material that formed Earth. The implications are profound. It means the raw ingredients for Earth's oceans may have been present much closer to home than anyone once thought. It also means that water delivery was likely a more common process than previously believed, not dependent on rare, chance impacts by comets, but woven into the very fabric of planetary formation. Yet this new picture does not erase comets from the story entirely. They may still have delivered other vital compounds, organic molecules, carbon-rich material, or trace amounts of water that contributed to Earth's chemistry. But their role was smaller and more nuanced than once imagined. The bulk of the water that makes life possible was not a distant gift from the outer reaches of the solar system. It was carried inward by humble, water-bearing asteroids, delivered piece by piece in a slow but steady rain of impacts. This shift in understanding illustrates how science often unfolds. A theory can stand for decades, elegant and convincing, until a small piece of evidence reveals a deeper truth. In this case, it was the subtle weight of a single neutron, the ratio of hydrogen to deuterium, that rewrote the story of Earth's oceans. And with that discovery, a new chapter began. The source of water was not as distant as scientists had once believed. It was closer, more ordinary, and perhaps more inevitable. Not all answers, however, come from above. As scientists began to look deeper, they realized that water's story was not written only in the sky. Some of its origins might lie far below, locked deep within the planet itself. Beneath the familiar surface of continents and seas, far below the crust we stand on, lies a realm that shaped Earth's earliest history in ways scientists are only beginning to understand. For much of the 20th century, the dominant story of our planet's water was one of delivery from afar, icy asteroids and wandering comets, striking a barren world and bringing the moisture that would one day become oceans. But as researchers have looked inward, they have uncovered another, equally compelling possibility. Perhaps Earth never needed cosmic help at all. Perhaps the ingredients for water were built into the planet from the very beginning, locked deep inside its interior and waiting patiently to rise. To trace this hidden story, we must journey far beneath the surface into the mantle, a vast, slow-moving layer of rock that stretches thousands of kilometers beneath our feet. This is not a static place. It is a world of immense pressure and heat, where minerals deform like putty and enormous convection currents churn over geological time. Here, in the earliest days of the planet, conditions were extreme enough to forge water in a way that seems almost alchemical. Hydrogen, the lightest and most abundant element in the universe, was present in the primordial dust and gas that built Earth. Some of that hydrogen became trapped inside the planet's forming minerals, sealed away in atomic lattices during the violent collisions that created the young world. Oxygen, meanwhile, was plentiful throughout Earth's rocky interior, bound into silicate minerals that make up much of the mantle's structure. When these two elements met in the crushing pressure and intense heat far below the surface, they combined to form water, not as liquid pools or icy pockets, but as molecules bound invisibly inside the minerals themselves. This water was not free to move or flow. It existed on a molecular level, locked into the structure of minerals like olivine and wadsleyite, hidden deep within the mantle's vast expanse. Yet, it was there all along, part of Earth's chemistry from the start. Over time, as the mantle shifted and circulated, this water began to move as well. Slow, Powerful convection currents pushed material upward toward the surface. Plumes of molten rock, rising from deep within, carried with them the water that had been trapped for millions of years. When this material neared the surface, the crushing pressure that once held the water inside minerals began to ease. As magma rose and cooled, the bound water was released. It escaped not as liquid, but as superheated steam, mixing with volcanic gases and bursting forth into the air through colossal eruptions. The early Earth was a far more volcanically active place than the one we know today. Volcanoes erupted with relentless force, pouring rivers of lava across the landscape and sending towering plumes of steam and gas into the thickening atmosphere. In those young skies, water began its journey from deep within the planet to the world above. At first, the heat near the surface was still too intense for steam to condense. But as millions of years passed, Earth continued to cool. The molten crust hardened into stable rock. The air thinned and temperatures fell. Eventually, the steam released by countless volcanic eruptions began to condense into droplets. Clouds formed, and for the first time, rain fell from the skies onto a planet that had never known it before. The rainfall was not a brief or passing event. Scientists believe it may have continued for millions of years, a ceaseless downpour that sculpted a new world. Droplets hissed and vanished on contact with still hot rock, then fell again. Craters left by ancient impacts filled with water. Valleys carved by cooling lava became riverbeds. Slowly, drop by drop, the water that had been born deep inside the planet pooled and gathered, forming the first seas. This theory, known as mantle outgassing, reveals that water's story on Earth may be as much about what rose from below as what arrived from above. It reframes the origins of oceans as an internal process, a release of water forged deep in the planet's interior, brought to the surface by the same geological forces that shaped continents and built mountains. Evidence for this still surrounds us today. Modern volcanoes continue to release large amounts of water vapor into the atmosphere, a faint echo of the colossal eruptions that transformed the early Earth. And the chemistry of volcanic gases sometimes shows subtle differences from water thought to have come from asteroids, hinting that part of our planet's water supply is truly homegrown. This inward-looking explanation does not exclude other sources. Water from the mantle and water delivered by asteroids could both have contributed to the oceans we know today. But it does suggest that Earth was never entirely dry, even before the bombardment from space began. The seeds of the oceans were already present, woven into the planet's interior from the very beginning. And while some of that deep water escaped to shape the surface, not all of it did. Much remains locked away beneath the crust, sealed in the planet's rocky heart. That part of the story belongs to the deep mantle itself, a hidden reservoir that we will return to when the time comes. For now, it is enough to know that when this buried water finally reached the open air, the planet learned how to rain. There was a time, far back in Earth's deep past, when rain was not a passing weather pattern, but the heartbeat of the planet itself. It was not the kind of rain that arrives and fades with the seasons, nor a storm that sweeps through and clears the skies. When the first rains came, they came to stay. Drop after drop, cloud after cloud, they fell without pause for millions upon millions of years, rewriting the face of a young world. By then, Earth was no longer the molten inferno it had been at its birth. The crust had hardened enough to form a landscape, though it was still fractured and restless. Volcanoes split the ground open and belched vast clouds of gas into the sky. Carbon dioxide, nitrogen, sulfur, and, above all, steam poured upward from the planet's interior, feeding a growing atmosphere thick with moisture. The steam did not dissipate, it rose and lingered, swirling into the upper reaches of the air, where the cooling planet could no longer hold it as vapor. At some critical moment, the balance tipped. Steam condensed into droplets, droplets gathered into clouds, and clouds, swollen beyond their limits, began to release their weight. Rain fell, boiled away, and fell again. Over and over, the same cycle played out. The first drops hissed angrily as they struck the still hot ground, vanishing into clouds of steam before they could pool or flow. But the process did not stop. More water vapor streamed upward from the volcanic vents below, and more clouds formed to replace those that had emptied. The sky had learned how to rain, and it would not stop. Each drop that struck the surface carried away a fragment of heat. Steam rising back into the sky drew even more energy from the ground. The process was slow, almost imperceptible on human timescales, but relentless. Gradually, the once scorching crust began to cool. Rain no longer vanished instantly on contact. It lingered for moments, then for minutes, then for hours. Eventually, it remained. Water began to gather wherever the landscape dipped or fractured. Shallow depressions became puddles, which deepened into pools. Craters, carved by ancient impacts, filled with dark, swirling lakes. In low-lying basins, water carved channels as it flowed, tracing the first fragile paths of rivers that had never existed before. This was no gentle sculpting. The rain, infused with carbon dioxide from the thick atmosphere, formed weak acids that reacted with the rocks beneath. Minerals dissolved and were carried away, altering both the surface and the chemistry of the water itself. This chemical weathering was a quiet but profound process. With every droplet that seeped into the ground, the planet's crust changed a little more. Elements essential for future biology, calcium, magnesium, phosphorus, and others were released from rock and washed into the growing pools. The first primitive soils began to form, thin and patchy, as erosion softened jagged surfaces and filled basins with sediment. The interplay of water and rock set the stage for the complex geochemical cycles that would one day sustain life. The rainfall did not let up. For millions of years, it continued without end, a ceaseless transfer of water from sky to ground and back again. As the surface cooled further, the water stopped evaporating as quickly. Lakes swelled and merged. Valleys deepened and widened. What had once been scattered pools began to link together, forming continuous networks of rivers and basins. Eventually, these waters united into vast, sprawling seas that stretched beyond the horizon. The young Earth was being transformed. Oceans thousands of kilometers wide and several kilometers deep spread across the planet's face. They cooled the crust even more, slowing the cycles of volcanic fury and moderating surface temperatures. The interaction between ocean and atmosphere began to stabilize the planet's climate, establishing feedback loops that would keep Earth habitable for billions of years to come. The rain's chemical work continued as well. The waters absorbed gases from the air, altering their composition and creating new pathways for energy and matter to circulate. Minerals dissolved in the water accumulated in the seas, forming a primordial chemical soup rich with the building blocks of future life. Ocean currents began to stir, distributing heat and nutrients around the globe. What had started as steam from volcanic vents was now an interconnected system of rivers, seas, and atmosphere, all locked in a dynamic dance. The relentless rain did more than cool the crust or fill basins. It sculpted the land into shapes we still recognize: river valleys that would later host deltas and floodplains, coastal shelves that would cradle future continents, and basins deep enough to cradle the vast oceans we know today. The continuous interaction of water with rock laid the foundation for Earth's geological cycles, the slow recycling of minerals, the burial of sediments, and the formation of the continents themselves. Each drop that fell carried a story older than any living thing. It carried heat from the planet's interior into the sky. It carried minerals from mountain peaks into ocean basins. It carried the memory of Earth's violent birth forward into a new era, one defined not by fire and stone, but by water and change. And so the rain fell, patiently and endlessly, for millions of years. It was more than weather. It was a planetary process, a shaping force that turned a once hostile landscape into one capable of nurturing oceans. It was the sound of a young world cooling, settling, and preparing for everything that would follow. Yet even this long and relentless storm was not the beginning of the story, for the rocks beneath our feet would soon reveal that water had arrived even earlier than we ever imagined. Long before continents had names and skies had color, before the first rivers traced their paths across stone, something quietly impossible was already happening on Earth. Deep in the rock record, locked inside crystals older than any mountain, there is a story that refuses to follow the script scientists once believed. It is a story of water arriving too soon, appearing when the planet should still have been too young, too chaotic, and far too hot to hold it. And it is a story that, once uncovered, forced us to question everything we thought we knew about the early Earth. Those ancient crystals, the ones we spoke of earlier, are more than just minerals. They are time capsules forged over 4 billion years ago when the planet was still in its violent infancy. Within them are chemical fingerprints that speak of liquid water, not steam swirling in volcanic skies, not frozen ice trapped in a passing comet, but actual water interacting with rock on the surface. That single detail changes the shape of Earth's early timeline, because if water truly existed that early, then almost every idea we have about when and how the planet became wet is out of order. The problem is not that scientists doubt the evidence. The zircon crystals are clear and consistent, their isotopic signatures unambiguous. The problem is that the timing they reveal seems to collide with every other part of the planet's story. According to the standard model, Earth's surface should still have been in turmoil during those early hundreds of millions of years. Asteroids and protoplanets were still colliding with enormous force, releasing enough heat to keep the crust thin and unstable. The atmosphere was thick with volcanic gases, and water, if present at all, should have existed only as vapor. Oceans, by this logic, could not have appeared until long after the violence faded. Yet the zircon record suggests otherwise. It implies that water was interacting with rock even while the sky was still thick with steam and space debris still hammered the planet's surface. If that is true, then the late arrival of water delivered only after the chaos ended cannot be the whole story. Perhaps the bombardment that was supposed to bring water came earlier than expected, seeding the planet with moisture before the surface was ready to hold it. Or perhaps the process of volcanic outgassing, which releases water from deep inside the mantle, happened faster and more efficiently than models predict. Both possibilities bend the accepted timeline, but neither fits it neatly. There is another layer to the puzzle. Outgassing alone, even if rapid, would have needed a stable crust to allow water vapor to cool and condense. If oceans really existed when these zircons formed, then the crust must have cooled far sooner than scientists thought possible. That cooling, in turn, might mean that Earth shed heat into space more quickly, or that impacts themselves helped strip away surface energy, allowing rock to solidify. But if that happened, then why do so many models show a molten surface persisting for far longer? Every solution opens another question, and every answer leads deeper into uncertainty. The implications stretch beyond the mechanics of cooling and bombardment. If liquid water was present so early, it means the hydrological cycle, the process of evaporation, condensation, and rainfall, may have started while the planet was still forming. That would mean clouds were already forming, storms already sweeping across the landscape, and rain already falling into basins long before Earth was supposed to be ready. It also hints that the early surface was more stable than once believed, capable of supporting bodies of water even as impacts reshaped the crust and volcanoes split it open from below. Some scientists have suggested that the only way to resolve this contradiction is to accept a more radical idea: that water was never something Earth acquired, but something it already possessed. Perhaps the hydrogen and oxygen that built our oceans were part of the raw material that formed the planet, bound within minerals and released almost immediately as the crust cooled. In that view, Earth did not become a wet planet over time. It was wet from the start, its oceans latent and waiting to emerge as soon as conditions allowed. The timing also changes how we think about habitability itself. If water was present when the planet was still young and unstable, then the conditions necessary for life may have existed earlier than anyone dared to imagine. The surface might not have been welcoming, but it was already experimenting with the chemical interactions that would one day lead to biology. The line between an uninhabitable rock and a living world becomes less clear when oceans appear so soon after the planet's birth. This contradiction between evidence and expectation remains one of the most intriguing questions in planetary science. On one side is the slow, orderly picture of Earth cooling, collecting water, and forming oceans over hundreds of millions of years. On the other is the Zircon record, which points to a wetter, more dynamic world almost from the very beginning. Both cannot be entirely right, yet both contain pieces of the truth. Somewhere between them lies the real story, one that scientists are still trying to piece together from fragments of rock and whispers of ancient water. The mystery is far from solved, but one thing is now certain. Water's story did not begin when the storms came or when icy bodies from the outer solar system struck the surface. It began earlier, deeper, and under stranger circumstances than anyone expected. Perhaps Earth did not need to wait for water to arrive. Perhaps it carried it all along from the very first moment it came into being, long before the first storms poured from a young sky, long before impacts seeded the planet with icy cargo from deep space. Earth may have already been wet. Not wet in the way we imagine today, with oceans glinting under sunlight or rivers winding through continents, but wet in its very bones. The idea, once considered unlikely, is now forcing scientists to rethink everything about the planet's origin. What if water was not something that arrived later, nor something forged only in the mantle's hidden depths, but something that was part of Earth from its very first breath? To follow this thread, we must travel back before Earth was a planet at all, to a time when the sun was still forming inside a cloud of gas and dust. Within that swirling disk, tiny grains collided and grew, forming larger and larger bodies known as planetesimals. These were the raw materials from which all planets were built, and their composition determined much about the worlds they would become. Some formed beyond the icy boundaries of the solar system, where water froze freely. Others condensed closer to the newborn sun, where heat stripped away volatile substances from their surfaces. But even here, water was not absent. Locked deep inside mineral structures, water molecules could survive even in regions far too warm for ice. This subtle detail changes the picture dramatically. If planetesimals that contained bound water formed in the inner solar system, then the materials that built Earth may have arrived already carrying their own supply. Water would not have been delivered later by distant comets or created solely by chemical reactions in the mantle. It would have been there from the start, woven into the crystalline frameworks of minerals that would one day fuse into continents, mountains, and crust. In this view, Earth was not a dry world waiting for water to arrive. It was born with water as part of its original recipe. The process by which this water became accessible was slow and inevitable. As Earth grew through countless collisions, the immense heat generated by impacts and radioactive decay melted much of its interior. Inside this molten environment, water that had once been locked inside minerals was freed. Some of it combined with silicates and oxides deep underground. Some was drawn upward by convection currents, trapped in rising magma, and some, perhaps a significant portion, escaped into the forming atmosphere as vapor, eventually condensing and falling back as rain. The difference between this view and earlier theories is subtle but profound. Instead of a planet transformed by external delivery, Earth becomes a world whose water was a built-in property of its formation. And instead of a clean division between delivered water from asteroids and internal water formed deep underground, the two ideas begin to merge. If water was embedded in the rocks from which Earth grew, then those rocks themselves acted as both delivery vehicles and internal reservoirs. The boundary between external and internal origin fades into a continuum where water was always part of the story, just locked in different forms at different times. Evidence for this picture comes from multiple sources. Meteorites, known as carbonaceous chondrites, believed to resemble the building blocks of the early Earth, contain significant amounts of bound water in some cases, several percent of their total mass. Their composition suggests that even in the early solar system's warmer regions, water-bearing minerals were widespread. Studies of volcanic gases released from deep within Earth also hint at ancient origins. Their chemical fingerprints differ from those expected if all water came from late bombardment, suggesting that at least part of Earth's water inventory has been present since the planet's earliest days. This perspective also reframes how we think about planetary habitability. If Earth's water was seeded during its assembly, then water may be a far more common ingredient of planets than once assumed. It would not require a lucky series of impacts to deliver it. Instead, any rocky world, forming from similar materials, could inherit water as a built-in feature, emerging already primed to host oceans once surface conditions allowed. Even planets that form close to their stars, once dismissed as too hot for water to survive, might carry vast amounts within their interiors, waiting for the right moment to escape. It is also possible that external deliveries and native water work together. Planetesimals that seeded Earth with bound water might have been followed by asteroids and smaller impacts that topped up the supply. Later, volcanic outgassing could have released additional stores from the mantle. Instead of a single event, the emergence of Earth's oceans becomes a layered story, a gradual accumulation, release, and recycling of water that began before the planet was even finished forming. If this is true, then water's history reaches back beyond Earth itself. It begins in the cold darkness of the molecular cloud that formed our solar system, when hydrogen and oxygen combined on the surfaces of dust grains. It continues as those grains merged into rocks, and as rocks became planetesimals, each one carrying its own hidden cargo of water locked within. By the time Earth coalesced, that water was already there, buried deep inside, waiting for heat and time to draw it out. In this way, the planet we live on was not a barren sphere transformed by a lucky delivery. It was a world-born weta planet whose capacity for rivers, clouds, and oceans was written into its structure from the very first moment of its creation. In the earliest chapters of Earth's history, creation and destruction were inseparable. The solar system itself was a place of chaos and collision where worlds were still forming and paths were uncertain. Among the many violent encounters that shaped our young planet, one stands apart in scale and consequence. It was a collision so immense that it reshaped the planet's destiny and left behind a companion that would quietly guide Earth's evolution for billions of years. That companion was the Moon. The story begins around 4.5 billion years ago, when Earth was still gathering material from the swirling disk of rock and dust that surrounded the young sun. Its surface was unstable and molten, and its skies were heavy with volcanic gases. Into this turbulent world came a wandering protoplanet, roughly the size of Mars. Scientists have given it a name, Theia, and its path eventually intersected with Earth's. The impact that followed released unimaginable energy, enough to melt rock, vaporize crust, and fling vast amounts of material into space. This violent collision might easily have been the end of Earth's story. Instead, it became the beginning of a new one. Much of the ejected debris remained nearby, swirling around the battered planet. Gravity gathered it together, clumping it into a single, growing sphere. Slowly, that sphere coalesced into a new celestial body, one that would orbit Earth for billions of years to come. The Moon had been born from fire and chaos. At first, it hovered far closer to Earth than it does now, looming massive and bright in the young sky. Its gravitational pull was stronger, its orbit faster, and its influence more immediate. Over time, as energy from the impact dissipated, the Moon began drifting outward, eventually settling into the familiar distance we see today. But even as it receded, its presence continued to shape Earth in subtle but powerful ways, especially in the story of water and stability. One of the most important of those influences was on Earth's axial tilt, the angle at which the planet spins as it orbits the Sun. That tilt governs the seasons, controlling how sunlight is distributed across the globe and how climates change over time. On planets without a stabilizing moon, the tilt can swing wildly. Mars, for instance, has no large moon to steady it, and its tilt has shifted dramatically over millions of years, sometimes standing nearly upright and at other times tipping steeply. Each shift brought radical climate changes, with ice caps melting, oceans freezing, and surface conditions transforming again and again. Earth's moon acts as a gravitational anchor, preventing such extremes. Its steady pull stabilizes the tilt, keeping it within a narrow range over vast stretches of time. This stability has allowed Earth to maintain predictable, gentle cycles of climate, the kind of balance in which water can remain liquid at the surface for billions of years. Without the moon's influence, Earth's tilt might have wandered through more erratic angles, leading to intense shifts in temperature. Oceans could have swelled and vanished with climate swings, and water might have cycled between extremes of vapor and ice far more often. The moon did not guarantee the existence of water, but it helped ensure that water could stay. Its influence was felt in other ways too. The moon's gravitational tug gradually slowed Earth's rotation, stretching what may once have been a 6-hour day into the 24-hour rhythm we now live by. A slower spin meant gentler winds and more stable weather systems, conditions that allowed the oceans to circulate more evenly and distribute heat around the globe. This moderation helped prevent extreme temperature gradients that could have destabilized early climates. The moon also gave Earth its tides. As it orbits, its gravity pulls on the oceans, causing them to rise and fall in a constant cycle. This tidal movement stirs nutrients, shapes coastlines, and prevents stagnant waters. It also had consequences for chemistry and, perhaps, for life itself. Along early shorelines, tidal cycles may have concentrated organic molecules in shallow pools, where they interacted and combined in increasingly complex ways. These repeated wet-dry cycles are thought by many scientists to have been crucial in the chain of events that eventually led to biology. The moon's presence also slowed Earth's geological heartbeat in another way. By moderating the spin and stabilizing the tilt, it indirectly affected how energy moved between the planet's interior, surface, and atmosphere. Stable rotation patterns influence the way tectonic forces operate, the way heat escapes, and the way water circulates over geological timescales. In countless small ways, the moon has been part of Earth's internal and external rhythms, shaping the conditions that allowed water to persist as liquid and support the emergence of complex systems. It is difficult to overstate how improbable this celestial partnership is. If Theia had missed Earth, or if the collision had been slightly different, the debris might never have formed a stable moon. The absence of that gravitational stabilizer would not necessarily have doomed Earth's water, but it would almost certainly have made it more volatile. Seas might have been shallower or more short-lived, climates more erratic, and conditions less favorable for the slow, steady evolution that followed. For billions of years, the moon has been a quiet but constant presence, shaping tides, steadying seasons, and moderating the rhythms of a watery world. It has no oceans of its own, no atmosphere to speak of, and yet it has been one of the most important partners in Earth's story of water. Its influence made this world less chaotic, its patterns more predictable, and its surface more welcoming to the rivers, lakes, and seas that would one day cradle life. That influence did not extend to every world. On our planetary neighbors, stability unfolded in different ways, and it is there, on Mars and Venus, that the contrast becomes clearest. In the beginning, there was little to distinguish them. Three rocky planets circled the same young sun, forming from the same cloud of dust and gas, built from the same elements forged in ancient stars. Earth, Mars, and Venus were siblings, born together in the crowded nursery of the inner solar system. They shared similar compositions, similar atmospheres, and, as far as scientists can tell, each one had water. For a brief moment in deep time, they may have all looked like worlds with oceans, clouds, and rain. Imagine them in those early days. Mars, a smaller, quieter world, likely wore thin rivers across its face and gathered lakes in broad basins beneath a pale pink sky. Venus, closer to the sun and wrapped in thick clouds, may have been home to shallow seas that shimmered on volcanic plains. Earth was still reshaping itself after the violence of its formation, but its surface too was beginning to glisten with water. Three young worlds, alike in their beginnings, seemed destined for similar futures. But the symmetry did not last. Slowly, over billions of years, their paths diverged. Today, they could not be more different. Earth is a world of deep blue oceans and a thriving hydrological cycle where water flows from sky to sea and back again. Mars is a frozen desert, scarred by dried riverbeds and empty deltas that speak of a wetter past. Venus is a planet of suffocating heat and crushing pressure, where the air itself is a toxic shroud and the surface is bone dry. All three started with water, yet only one still holds it in abundance. The reason lies not in how much water they had, but in how well they could keep it. Mars's story is one of gradual loss. Smaller than Earth, with only about half its diameter, Mars never had the same gravitational pull to hold onto a thick, protective atmosphere. Early on, conditions were promising. Geological evidence shows networks of river valleys, deltas, and sedimentary layers that formed in the presence of flowing water. Ancient shorelines hint at a vast northern ocean that may once have covered much of the planet's surface. For hundreds of millions of years, Mars may have supported a mild, wetter climate. But deep inside, Mars cooled faster than Earth. With its interior heat fading, the dynamo that powered a magnetic field weakened and eventually died. Without that shield, the solar wind, a continuous stream of charged particles from the sun, began to erode the Martian atmosphere. Over time, it thinned to a fragile veil, unable to trap heat or protect surface water. As the air pressure dropped, liquid water evaporated and drifted into the sky, where sunlight broke its molecules apart. The light hydrogen escaped into space, leaving the heavier oxygen behind. The rivers dried, the lakes vanished, and Mars became the cold, arid world we see today, its watery past etched into the landscape like a ghost of what once was. Venus, by contrast, did not lose its water quietly. It started with an advantage, a thick atmosphere and possibly shallow oceans that covered parts of its surface, but it was cursed by proximity. Orbiting much closer to the Sun, Venus received far more energy than Earth, and that extra heat pushed its climate toward instability. Even small increases in temperature accelerated evaporation, and the water vapor that filled the air amplified the effect, trapping more heat and causing even faster evaporation. This runaway feedback loop spiraled out of control. The oceans boiled into the sky, and the thickening blanket of water vapor turned Venus into a greenhouse world. In the upper atmosphere, sunlight split water molecules, and hydrogen escaped into space. As the last traces of water vanished, carbon dioxide, once dissolved in the oceans, accumulated unchecked. The atmosphere grew denser and hotter, reaching pressures more than 90 times that of Earth's, and temperatures high enough to melt lead. Venus became a furnace, a planet once perhaps veiled in mist, now sealed beneath a suffocating sky. Earth's fate was more forgiving. Its larger size allowed it to hold onto a thick atmosphere, and its molten core continued to generate a magnetic field that deflected much of the solar wind. Most importantly, Earth's distance from the Sun placed it in a narrow band where water could exist as a liquid for billions of years. Here, evaporation and condensation could reach a natural balance. Oceans did not boil away as they did on Venus, nor did they freeze and vanish as on Mars. Instead, water cycled gently between sea, sky, and soil, shaping landscapes and sustaining conditions that remained stable enough for life to emerge. The great divergence between these three siblings was not just a matter of geography or chemistry. It was a story of scale, distance, and timing of how planetary size, orbital position, and internal heat combined to determine the fate of water. Mars was too small to keep what it had. Venus was too close to the Sun to remain stable. Earth, balanced delicately between the two extremes, found itself in a sweet spot where water could persist. And yet, even this balance was not the whole story. Retaining water required more than the right size and the right distance. It also required protection, a shield that would guard the atmosphere and preserve the delicate balance that water needed to survive. How that protection worked, molecule by molecule, is the next part of the story. When Earth was still a young and restless world, its surface was a landscape of fire and stone. Volcanoes split the ground open with rivers of molten rock, and impacts from the last waves of planetary debris lit the skies with catastrophic force. But beneath all that chaos, far deeper than any eruption could reach, something more subtle and more crucial was happening. It was a process that would quietly determine whether water could ever stay here at all. Deep in Earth's interior, more than 3,000 kilometers below the crust, heavy elements like iron and nickel were sinking inward, drawn by gravity toward the planet's center. The immense pressure and heat there kept much of this metallic heart in a molten state. As Earth rotated, the churning motion of that liquid iron created powerful electric currents. And from those currents, an invisible shield emerged, a magnetic field that would stretch far beyond the surface, reaching tens of thousands of kilometers into space. It was not something anyone could see, yet it would become one of the most important features Earth would ever possess. The sun, even in its youth, was far from gentle. It constantly released a stream of charged particles into space, a high-speed river of plasma called the solar wind. These particles raced outward in all directions, colliding with anything that crossed their path. For planets without protection, the result could be devastating. The solar wind can erode a planet's atmosphere, stripping it away molecule by molecule. Without an atmosphere, water cannot remain stable. It either boils into space or breaks apart under the relentless glare of ultraviolet light. Earth was not defenseless. The magnetic field generated deep within its core carved out a protective bubble in space known as the magnetosphere. This invisible barrier deflected much of the solar wind, redirecting it around the planet rather than allowing it to slam directly into the atmosphere. Inside that shield, the air could thicken and persist, and with that air came pressure, temperature, and the delicate balance that allowed water to exist as a liquid on the surface. But the magnetosphere alone was not enough. A strong magnetic field reduces atmospheric loss, but it cannot stop it entirely. Whether a planet can hold on to its air, and therefore its water, depends on several interconnected factors: the composition and density of the atmosphere, the temperature of its upper layers, the level of ultraviolet radiation from the sun, and the overall mass of the planet itself. Together, these forces determined how Earth's story would unfold. Early in its history, Earth's atmosphere was nothing like the oxygen-rich air we breathe today. It was a dense mix of carbon dioxide, nitrogen, water vapor, and traces of other volcanic gases. That atmosphere did three essential things. It trapped enough heat to prevent the planet from freezing. It created surface pressure high enough for water to stay liquid, rather than instantly evaporating into space. And it acted as a protective layer, absorbing much of the sun's harmful radiation before it could tear water molecules apart. The interaction between the atmosphere and the magnetosphere was delicate but vital. As the solar wind swept across the magnetosphere, most of it was diverted away, but some particles slipped through, colliding with the upper atmosphere and transferring energy. These collisions could heat the air, causing lighter elements like hydrogen to escape. Here, again, the atmosphere's composition mattered. A denser mix of heavier gases slowed that escape. Meanwhile, Earth's relatively large size ensured gravity could hold on to much of the atmosphere that tried to drift away. Water molecules in the upper atmosphere were still vulnerable to sunlight. Ultraviolet radiation split them apart, freeing hydrogen atoms that could escape into space. This process, known as photodissociation, is one of the primary ways planets lose water over time. The magnetosphere could not stop it, but by limiting the amount of atmosphere eroded by the solar wind, it slowed the overall rate of loss. Over millions of years, that difference mattered. The amount of hydrogen that escaped from Earth was far lower than what leaked from planets like Mars or Venus. The contrast is clearest when we look at those worlds today. Mars once had rivers and perhaps even seas, but its smaller size meant its core cooled quickly. The magnetic field shut down, leaving the planet exposed. Solar wind stripped away much of its atmosphere, and what remained was too thin to support liquid water. Venus may once have been wet too, but without a robust magnetosphere, its upper atmosphere was bombarded by the solar wind and intense ultraviolet radiation. Water molecules broke apart, hydrogen drifted into space, and the planet's oceans were lost. Earth's outcome was different. Its molten outer core stayed active, keeping the magnetic field alive. The magnetosphere deflected the worst of the solar wind, and the atmosphere remained thick enough to shield water from destruction. Together, these forces created a stable equilibrium, one that allowed oceans to collect, rivers to flow, and rain to fall for billions of years. Even today, the same processes continue. Solar particles slam into the magnetosphere and are pushed aside. High in the atmosphere, some hydrogen still slips away, molecule by molecule, into space. But the balance holds. Earth retains enough water to fill its oceans many times over, and the cycle between evaporation, condensation, and rainfall continues unbroken. The survival of water on Earth was never the work of a single factor. It was the product of a deep planetary engine driving a magnetic shield, of a thick and evolving atmosphere, of gravity strong enough to hold that air in place, and of solar conditions that allowed liquid water to persist. Each piece depended on the others, and together they shaped a world where water could stay, a world where oceans would not vanish into the void, but remain, flowing and cycling for billions of years. Beneath the thin shell of continents and seas that we call home, there is a world so alien and remote that even our most powerful instruments can only glimpse it indirectly. It lies far below the ocean floor, beyond the crust, deeper even than the vast mantle currents that slowly churn beneath our feet. Down there, hundreds of kilometers below the surface, water exists in a form unlike anything we know on the surface. It is neither liquid nor ice. It is bound invisibly into the crystal structure of minerals, locked away inside the rocks that make up Earth's deep interior, and it may be one of the planet's most important hidden reservoirs. For most of history, the story of water was told only as a surface story. It was something we saw and measured in rivers and lakes, in clouds and rainfall, in seas that stretched from horizon to horizon. Even when scientists learned that water could rise from volcanic eruptions or be delivered from space by comets, they still pictured it as part of a cycle that took place above the crust, a loop between ocean and atmosphere. But as technology advanced and geologists learned how to read the clues carried up from deep within the planet, a new and more mysterious chapter of water's story began to unfold. The first hints came from tiny inclusions inside volcanic minerals. These crystals, brought up to the surface by violent eruptions, had formed hundreds of kilometers down under crushing pressures and searing temperatures. Inside them, scientists discovered traces of water not as droplets or pockets of liquid, but as individual hydrogen and oxygen atoms woven into the atomic lattice of the minerals themselves. It was proof that water was not just present at the surface or in the crust. It was part of the mantle too. One discovery in particular transformed our understanding. Deep within a layer of the mantle, known as the transition zone, a region that begins roughly 400 kilometers beneath the surface and extends down to about 700 minerals, undergo dramatic changes under the immense pressure. One of those minerals is ringwoodite, a high-pressure form of olivine with a remarkable property. It can hold significant amounts of water inside its crystalline structure. Samples of ringwoodite, carried to the surface by ancient plumes of mantle rock, revealed water contents far higher than anyone had expected. These findings led scientists to a striking possibility. Based on mineral physics and the behavior of ringwoodite, the mantle's transition zone may be capable of storing multiple ocean equivalents of water within its minerals. This is not a measured inventory. No one can yet say exactly how much water is down there, but it shows that the deep earth has the capacity to hold staggering amounts. If even a fraction of that potential is realized, then far more water could be hidden beneath our feet than flows on the planet's surface. The water stored in the mantle does not sit still forever. Earth is a restless planet, and the motion of its tectonic plates acts as a conveyor belt that slowly cycles water between surface and interior. When oceanic crust slides beneath another plate in a process called subduction, it carries with it sediments and minerals saturated with water from the seafloor. As these materials descend into the mantle, the water becomes part of the mineral structure, locked into the rock and carried deeper still. For millions or even billions of years, that water can remain imprisoned in the mantle's minerals, but the cycle eventually reverses. In other places, rising plumes of molten rock carry some of this deeply buried water back upward. When magma reaches the surface through volcanic eruptions, the water is released as steam. It condenses into clouds, falls again as rain, and replenishes the oceans and rivers above. What seems on the surface to be a closed and simple water cycle, evaporation, condensation, precipitation, is in reality part of a much larger planetary system, one that stretches from the atmosphere to the mantle and back again. This exchange may even help regulate Earth's water supply over geological timescales. As tectonic plates drag water down and volcanic eruptions return it to the surface, a slow equilibrium emerges. It prevents the oceans from shrinking too much through loss to space or growing uncontrollably from continuous volcanic outgassing. Over billions of years, this deep water cycle may have been one of the key reasons Earth's oceans have remained a stable and enduring presence. The presence of water deep in the mantle also shapes the planet in other ways. Water within minerals can change how rocks melt, making it easier for magma to form and influencing where volcanoes erupt. It can affect the movement of tectonic plates, lubricating faults, and altering how continents drift. It even plays a role in how heat flows through the planet's interior, subtly influencing Earth's long-term evolution. The idea that so much water might be hidden in the depths beneath our feet changes how we see the planet. It reminds us that the oceans we know, the ones that cover most of the surface and define so much of life's story, are only part of a far larger system. They are the visible tip of a deep and ancient circulation that links the sky above to the rock far below. Scientists are only beginning to understand how this hidden water shapes Earth's past and future. Every fragment of ringwoodite brought to the surface, every trace of hydrogen trapped in a mantle crystal, tells us that the story of water is not just written on the surface. It is written deep within the planet, sealed inside the very rocks that hold the continents aloft, waiting to be released again into the endless cycle that connects Earth's interior to its seas. Once the great rains had fallen and the first oceans had settled into their basins, Earth entered a new and quieter chapter of its story. The planet that had once been fire and fury was now wrapped in water, its surface shimmering under a pale young sun. But this new blue world was not yet alive. It was still a silent place, an ocean planet filled with potential but empty of purpose. That would soon change, because water, once present, is never just water. It is a solvent, a builder, a catalyst, and beneath its calm surface, something extraordinary was beginning to stir. Far below the waves, where sunlight could not reach and the ocean floor stretched in endless darkness, The crust of the Earth was still restless. The interior of the planet had not cooled completely. Heat from its molten heart pulsed outward, forcing magma upward through cracks in the seafloor. At certain points, this hidden energy met the cold embrace of seawater. The result was something entirely new: hydrothermal vents. These vents were not gentle springs, but roaring fountains of water heated to hundreds of degrees. Seawater seeped into cracks in the crust, was superheated by underlying magma, and shot back into the ocean, loaded with dissolved minerals and chemicals from deep within the earth. What erupted was a dark, mineral-rich plume that billowed like underwater smoke. The places where these plumes emerged became landscapes of towering chimneys and mineral spires, rising like strange cathedrals from the ocean floor. Scientists would one day call them black smokers for the dark clouds they released into the water. The world around these vents was unlike any other environment on Earth. The temperature gradient was extreme. Near the vent openings, water could reach more than 300 degrees Celsius, yet just a few meters away it was close to freezing. Chemical reactions ran wild in this environment, driven by the energy of the hot water and the minerals it carried. Iron, sulfur, and other elements mixed with seawater, producing gradients of energy that could be harnessed by chemical reactions. The seafloor became a natural laboratory, where matter was constantly broken down and rebuilt in new ways. In this deep, sunless realm, life may have found its first foothold. Modern experiments have shown that the chemical conditions near hydrothermal vents can produce the building blocks of life. Simple molecules like amino acids and nucleotides that are essential for proteins and DNA. These molecules form more easily in the presence of minerals like iron and nickel, which were abundant in vent fluids. The porous walls of the vent chimneys may have even acted like primitive cell membranes, concentrating these molecules and allowing them to interact. Over time, these reactions could have assembled more complex structures, eventually leading to the first self-replicating systems. This idea that life's origins were tied to hydrothermal vents is more than speculation. It is supported by the fact that some of the most ancient forms of life still living today are found in vent ecosystems. These organisms, known as extremophiles, thrive in conditions that would kill most other life forms. They do not rely on sunlight or photosynthesis. Instead, they draw energy from chemical reactions, using compounds like hydrogen sulfide to fuel their metabolism. This process, called chemosynthesis, mirrors the kind of chemistry that may have sparked the earliest forms of life billions of years ago. The communities around hydrothermal vents are some of the most remarkable ecosystems on Earth. Tube worms taller than a person, blind shrimp, and bacteria-rich mats flourish in total darkness, surviving entirely on the chemical energy rising from the planet's interior. These organisms exist independently of the sun, proving that life does not need light to thrive. This discovery has changed how scientists think about the universe, because if life can exist here in such an alien environment, it might also exist in similar places elsewhere, perhaps beneath the icy shells of moons like Europa or Enceladus, where hydrothermal vents could heat subsurface oceans far from any star. Hydrothermal vents did more than provide the raw materials for life. They also created gradients differences in temperature, pH, and chemical concentration that allowed primitive systems to capture and store energy. These gradients are the foundation of metabolism, the process that powers every living cell today. Even now, billions of years later, the basic chemistry of life still reflects its deep ocean origins. Cells use proton gradients across membranes to produce energy, echoing the conditions that once existed at those ancient vents. The emergence of hydrothermal activity transformed the oceans from passive bodies of water into active chemical engines. They became places where geology and chemistry intertwined, where energy from the planet's heart mixed with the building blocks of matter. In that mixture, the first whispers of biology began. The earliest life on Earth may have been nothing more than simple molecules bound together by chance, but around these vents, chance was not rare. It was constant, driven by the ceaseless churn of heat and water and rock. Each reaction was a small experiment, and given enough time, hundreds of millions of years of time, those experiments gave rise to something new. The oceans had already reshaped Earth's surface, carving rivers and forming clouds. Now they were reshaping its destiny. From lifeless chemistry came the beginnings of metabolism, replication, and evolution. From the dark cracks of the ocean floor, the story of life began to unfold. And all of it started with water not just as a liquid, but as the stage upon which matter learned to become alive. Once the first oceans settled across Earth's surface and the chemistry of life began to stir in the deep, water's influence did not end there. It was only beginning to reveal the extent of its power. Water, so soft and unassuming on the surface, became one of the most transformative forces in the planet's history. It shaped continents, carved mountains, and even helped build the very crust beneath our feet. Without it, the solid face of our world would look nothing like it does today. To understand how deeply water shaped Earth, we have to look beneath the surface, to the slow, ceaseless motions of the planet's crust. Earth is not a static sphere of rock. Its outer shell is broken into enormous slabs called tectonic plates that float on the mantle beneath them. Over millions of years, these plates drift, collide, and pull apart. They carry continents across the globe like rafts and rearrange the positions of oceans and mountains. And water, quietly and invisibly, is the reason this movement can happen at all. In the early days of our planet, before water softened its surface, Earth's crust was rigid and unyielding. It lacked the flexibility needed for tectonic plates to slide and shift. But when water seeped into the rocks, it acted like a lubricant. It lowered the melting point of minerals and made the solid crust easier to bend and move. With water woven into its structure, the crust could fracture, flow, and sink. Subduction zones, where one plate dives beneath another, became possible. Rifts opened where plates pulled apart, creating new seafloor. Earth was no longer a frozen shell. It became a dynamic, restless world. This movement was more than a geological curiosity. It was the key to building continents. Deep within the mantle, where heat and pressure are intense, rocks melt into magma. As plates sink and melt, water carried down with them helps form magma that is lighter and more buoyant. This buoyant magma rises toward the surface and solidifies into new crust. Over time, these repeated eruptions built up land masses layer by layer. It was a slow process, measured not in centuries, but in hundreds of millions of years. Yet without water to aid the cycle of melting and rising, continents might never have formed. Volcanoes, too, owe much of their power to water. When water mixes with magma beneath the surface, it turns into steam under extreme pressure. That pressure can drive explosive eruptions, sending ash and lava across vast distances. These eruptions are destructive, but they are also creative. They bring minerals from deep within Earth up to the surface, enriching the crust and the soil above it. Entire mountain ranges and island chains were born this way, their origins traced back to water buried deep within the planet's interior. Once continents rose above the waves, water continued its quiet work, shaping the world in new ways. Rain and rivers began the long, patient process of weathering rock. Drop by drop, they dissolved minerals and broke apart stone, turning towering peaks into soil and sand. Rivers carved deep valleys and canyons, creating pathways for ecosystems to form. Over time, these processes sculpted landscapes of astonishing variety: plains and plateaus, basins and mountain chains, coastlines that curved and shifted with the pull of tides. Water's role extended even further. As it weathered rocks, it released essential nutrients like phosphorus and iron into rivers and oceans. These nutrients nourished early microbial life and set the stage for more complex ecosystems to evolve. Without the steady hand of water shaping the land and feeding the seas, life's story would have been very different. Even the cycles that regulate the planet's climate are tied to water's geological influence. The movement of tectonic plates exposes fresh rock, which reacts with carbon dioxide in the air. This chemical weathering draws greenhouse gases out of the atmosphere and helps stabilize the climate over geological timescales. In this way, water indirectly maintains the delicate balance that makes Earth habitable. The continents we stand on today are monuments to water's quiet strength. They were lifted by its presence deep underground, carved by its flow on the surface, and sustained by its endless cycles of erosion and renewal. Without water, Earth would likely resemble the barren, rocky surfaces of Mercury or the lifeless plains of Mars. It might still have a crust and a mantle, but it would lack the dynamic processes that build mountains and shape valleys. Every landscape we know, from the jagged peaks of the Himalayas to the rolling plains of Africa, from the vast river deltas of Asia to the canyonlands of North America, carries water's signature. It is written into the layers of rock, etched into the curves of valleys, and hidden within the minerals beneath our feet. Even the continents themselves, which seem so solid and enduring, are in many ways creations of water. In the deep history of our planet, water was never just a liquid that filled oceans or nourished life. It was an architect. It softened stone, moved mountains, and lifted land from the depths of the sea. And with every collision, every eruption, every drop of rain that fell from the young sky, it continued its patient work, shaping a world that would one day cradle forests, rivers, and civilizations. The continents are not merely land. They are the memory of water, frozen in stone. There were moments in Earth's deep past when the planet seemed to come perilously close to stopping the story of life altogether. Long after the first oceans had spread across its surface, long after the earliest microbial colonies had begun their slow work in the dark waters, Earth plunged into a cold so complete and so enduring that it transformed the entire planet into something strange and alien. Twice in its ancient history, our world nearly froze over, not just in its polar regions, but almost entirely, from horizon to horizon. The first of these near total freezes began more than 2 billion years ago during a period scientists call the Huronian glaciation. The second arrived roughly 700 million years ago during the Cryogenian period, and it was even more severe. Scientists call these events Snowball Earth because from space, our planet would have appeared as a pale, frozen orb, its continents buried beneath vast glaciers, and its seas sealed beneath sheets of ice. Yet even this name, dramatic as it is, tells only part of the story. Ice likely spread to near global coverage, but many researchers believe thin patches of open water, called equatorial leads, may have persisted near the planet's waistline, where liquid water remained in contact with the air. To understand how such a world could form, we need to look at the balance that governs a planet's climate. Earth's temperature is a delicate equilibrium between the heat it receives from the sun and the heat it loses back into space. Greenhouse gases like carbon dioxide act as an insulating blanket, trapping warmth and keeping the surface habitable. But when that balance tips, even slightly, it can trigger a chain reaction with world changing consequences. During the first Snowball Earth, that balance shifted dramatically. Volcanic activity slowed, and the carbon dioxide that had once poured into the sky diminished. Without that greenhouse blanket, heat began to leak into space, and global temperatures fell. Ice advanced outward from the poles, bright and reflective, bouncing more sunlight away and cooling the planet even further. The colder it became, the more ice formed a self reinforcing loop that pushed Earth into a deep and prolonged freeze. The seas that had once been alive with microscopic organisms began to stiffen under a growing shell of ice. What started as frozen caps at the poles spread outward until it reached nearly every corner of the planet. Oceans were sealed beneath thick, grinding slabs. Continents vanished beneath glaciers kilometers deep. The air grew thin and frigid, and sunlight bounced uselessly from a reflective surface that stretched almost from pole to pole. Yet even in this seemingly frozen tomb, water refused to disappear. Beneath the ice, pressure from the layers above kept the deeper oceans from freezing. Heat from Earth's interior seeped upward from the crust below, sustaining pockets of liquid water. Around hydrothermal vents on the seafloor, ancient microbial communities endured, surviving on chemical energy rather than sunlight. Life persisted too, in thin films of brine, trapped between layers of sea ice, or in small, scattered melt zones beneath the glaciers. The surface might have been locked in silence, but deep below, the story of life continued. The second great glaciation, the cryogenian Snowball Earth, was even more extreme. It began about 715 million years ago and may have lasted tens of millions of years. The trigger may have been a combination of factors: continents drifting near the equator and reflecting more sunlight, shifts in ocean circulation, or another sharp decline in atmospheric carbon dioxide. Whatever the cause, the effect was devastating. Ice swept across the globe, possibly reaching even the tropics. For life, this was one of the most difficult chapters in Earth's history. Photosynthesis faltered under the weight of the ice, starved of the sunlight it needed. Ecosystems collapsed into isolated refuges where only the hardiest microbes survived. And yet, those survivors did not merely wait out the cold. They adapted. They evolved strategies for enduring extreme darkness, low temperatures, and scarce nutrients. Evolution, slowed but not stopped, continued to sculpt the living world in hidden places beneath the ice. Eventually, the planet's own geology provided a way out. Even in the depths of the freeze, volcanoes continued to erupt, releasing carbon dioxide into the air. Over millions of years, the gas built up, thickening the atmosphere and trapping more heat. Gradually, temperatures rose. The feedback loop reversed itself. Ice began to melt, exposing darker surfaces that absorbed more sunlight, which in turn accelerated the thaw. Cracks widened across frozen seas. Sheets broke apart and drifted. And finally, liquid water returned to the open air. The thaw that followed was as dramatic as the freeze itself. Torrents of meltwater surged across the continents, carrying minerals and nutrients into the seas. Oceans roared back to life, and with them came sunlight, energy, and opportunity. Many scientists believe this sudden release from global ice was a turning point in Earth's biological story, paving the way for the rise of complex multicellular organisms. Snowball Earth reminds us that water is not a passive presence. It is a force capable of reshaping the entire planet, driving it to climatic extremes and then helping it recover. Even when the surface world lay sealed beneath frozen seas, water persisted flowing beneath the ice, sustaining ecosystems in darkness and biding its time, and when warmth returned, it was water that carried the planet forward once again, sweeping life into new forms and setting the stage for the next great chapters of Earth's unfolding story. For billions of years, Earth's skies were nothing like the soft blue dome we know today. They were heavy and dim, filled with gases like methane and carbon dioxide, and almost completely devoid of oxygen. The air was not only unbreathable but also hostile to most forms of life we are familiar with. Yet, in the depths of the planet's oceans, a slow and extraordinary transformation was beginning, one that would eventually change the chemistry of the entire atmosphere and alter the course of life forever. It all started with water. By this time, Earth was no longer the molten world of its youth. The surface had cooled, continents had risen, and oceans stretched across most of the planet. Simple life had already taken root, microscopic organisms that drifted through the water, feeding on the chemical energy of their surroundings. These early life forms were primitive, yet they held the key to a process that would transform the world: photosynthesis. Photosynthesis is one of nature's most remarkable tricks. It is the process by which certain organisms capture energy from sunlight and use it to build the molecules they need to survive. But there is another crucial part of this process, one that changed everything. During photosynthesis, water molecules are split apart. From each molecule, oxygen is released as a byproduct, drifting upward and mixing into the surrounding environment. The first organisms to master this ability were cyanobacteria, tiny single-celled microbes that floated near the sunlit surface of the ocean. They had no idea of the monumental impact they were having, but their slow, steady activity was rewriting the atmosphere. Over millions of years, countless cyanobacteria absorbed sunlight, split water, and exhaled oxygen. Drop by drop, breath by breath, they were reshaping the world. At first, this oxygen did not reach the air. The oceans were rich in dissolved iron, and the newly produced oxygen quickly reacted with it, forming iron oxides that sank to the seafloor. These reactions left behind vast layers of reddish rock, known today as banded iron formations. They are silent geological records of a time when the oxygen produced by life was still being captured by the planet's chemistry. But eventually, after millions of years, the iron was used up. Oxygen could no longer be locked away so easily. It began to accumulate in the water, then bubble upward into the air. The change was slow at first, almost imperceptible, but it was relentless. What followed was one of the most dramatic shifts in Earth's history: the Great Oxidation Event. The Great Oxidation Event began around 2.5 billion years ago, and it was not a gentle transition. As oxygen levels rose, they triggered sweeping chemical reactions across the planet. Methane, a powerful greenhouse gas that had helped keep Earth warm, reacted with the new oxygen and was broken down. This caused global temperatures to fall, perhaps even triggering one of the planet's early glaciations. Minerals on land and in the oceans changed their composition. Entire ecosystems, which had evolved in an oxygen-free world, were thrown into crisis. For many early life forms, oxygen was not a gift, but a poison. Vast numbers perished, unable to adapt to the new conditions. Yet even as it disrupted the world that had existed before, oxygen opened the door to something far greater. With oxygen came the possibility of new forms of metabolism, ways of releasing energy from food that were far more efficient than anything possible in an anoxic world. This extra energy allowed organisms to grow larger, become more complex, and evolve new capabilities. It laid the groundwork for the rise of multicellular life and, eventually, for the diversity of plants and animals that would come to dominate the planet. Oxygen also had another profound effect. High in the atmosphere, some of it transformed into ozone, a molecule that shields the surface from harmful ultraviolet radiation. With this new protective layer, life could safely venture closer to the sunlit shallows and, much later, even onto land. The stage was being set for an entirely new chapter in Earth's story. The transformation was not quick. It took hundreds of millions of years for oxygen levels to rise significantly and for ecosystems to adapt to the new conditions. But the changes that began with the splitting of water molecules by humble microbes would echo through all of Earth's future. Every breath taken by every animal, every flame that burns, every rusting nail and weathered stone is a direct consequence of that ancient process. What began as a simple chemical reaction deep in the oceans became a planetary revolution. Water, once only a liquid that carved rivers and cradled life, became the source of the very air that sustains it. Cyanobacteria had no plan, no intention, but their relentless work transformed Earth from a world of suffocating gases into a living, breathing planet. And in that transformation lay the foundation for forests, for animals, and for every living thing that would ever walk beneath an oxygen-rich sky. If you were to look at Earth from space, you would see a world dominated by water, a planet wrapped in a thin, glimmering shell of oceans. But those waters are more than just a home for life. They are the planet's memory. Across billions of years, they have absorbed, recorded, and stored the history of everything that has happened here, the violent, the quiet, the catastrophic, and the subtle. Every wave that crashes on a shore and every raindrop that falls into the sea carries with it traces of the past, written in forms that scientists are still learning how to read. Unlike rocks, which can be buried or destroyed, water is always in motion, circulating through the air, the ground, and the ocean depths. As it moves, it touches everything. It dissolves minerals from ancient mountains, captures gases from volcanic eruptions, and absorbs particles from passing asteroids. It carries fragments of the past across the planet, layering them into sediments on the seafloor. In this way, Earth's water becomes an archive, one that never stops growing. One of the most powerful ways scientists read this watery memory is through isotopes, the subtle variations in atoms that act like fingerprints of past events. For example, oxygen comes in slightly different forms, known as isotopes, and the ratio of these isotopes in water changes depending on the temperature and climate at the time. By drilling into ancient layers of seafloor mud and analyzing these ratios, scientists can reconstruct what Earth's climate was like millions of years ago. They can see when ice sheets advanced and retreated, when deserts bloomed, and when tropical rainforests flourished. These isotopic clues reveal stories that would otherwise be lost. They show, for example, how during the Great Ice Ages, lighter isotopes evaporated more easily, leaving heavier ones behind in the ocean. They show how periods of intense warmth changed the composition of rain and rivers, altering the signature of water locked in shells and sediments. With careful study, scientists can trace temperature swings that unfolded over hundreds of thousands of years and piece together a timeline of Earth's changing climate. The oceans also record the planet's more violent moments. When a massive asteroid slammed into Earth 66 million years ago, it vaporized rock and scattered debris across the globe. Some of that material settled into the oceans, forming a thin layer of clay, rich in rare elements like iridium, an element more common in asteroids than in Earth's crust. That layer, now buried beneath millions of years of sediments, is still there, a silent marker of the day the dinosaurs vanished. Volcanic eruptions leave their signatures too. When supervolcanoes erupt, they spew ash, gases, and minerals into the atmosphere. These particles eventually settle into the oceans, where they form distinct layers on the seafloor. By studying these layers, scientists can pinpoint the timing of ancient eruptions and measure their impact on global climate. They can even trace how volcanic gases altered ocean chemistry, leading to events like mass extinctions or shifts in marine life. Sediments also preserve traces of life itself. The remains of microscopic organisms, such as foraminifera and diatoms, accumulate over millions of years on the ocean floor. Each layer represents a snapshot of the world. At that time, its temperature, its nutrient levels, and even the amount of carbon dioxide in the air. The size, shape, and chemical makeup of these fossils tell scientists how ecosystems responded to global events. They reveal when oceans were warm and rich with life, and when they were cold and nearly barren. Even the water itself, trapped in ice cores from polar regions, carries ancient messages. Tiny bubbles within those layers contain air from distant ages, allowing scientists to measure the composition of Earth's atmosphere hundreds of thousands of years ago. By comparing these ancient records with modern data, they can trace the rise and fall of greenhouse gases and understand how the planet's climate system has evolved. All of this information, the isotopes, the sediments, the fossils, the gas bubbles, comes together to form a planetary diary. It is not a straightforward story, but rather a complex tapestry woven from countless events over billions of years. Reading it requires patience and precision, but the rewards are immense. Through this watery record, scientists can travel back to moments long before humans existed. They can see how continents shifted, how sea levels rose and fell, and how the rhythms of Earth's orbit shaped cycles of ice and warmth. Sometimes, the story written in the oceans is dramatic, marked by sudden upheavals like asteroid strikes or massive volcanic eruptions. At other times, it is subtle, a slow drift in temperature or a gradual change in ocean currents. Yet all of it is part of the same long narrative, the unfolding history of a planet constantly reshaped by water. Every drop of rain that falls today, every wave that laps against a shore, carries echoes of this vast history. They are part of the same cycle that has been running since Earth's beginning, linking past and present in an unbroken chain. The oceans remember the fire and the ice, the extinctions and the blooms, the rise of continents and the fall of ancient seas. And by learning to read their language, we glimpse not only where our planet has been, but also where it might be headed. Billions of years before the last wave breaks on a barren shore, the story of Earth's water will already have begun its long, slow unwinding. It will not happen in a sudden rush or with a single catastrophic event. It will unfold quietly, almost imperceptibly, over spans of time so vast that no single generation could ever notice the change. The oceans will still shimmer in the sunlight, rain will still fall from the clouds, and rivers will still carve their paths through stone. Yet beneath the surface of this familiar world, the machinery that sustains those waters will be shifting, slowing, and faltering. It will begin deep within the planet, where heat has driven Earth's internal rhythms since its birth. That heat has always powered volcanic eruptions, fueled mantle convection, and melted rocks into magma that carried water upward from the depths. But no planet can burn forever. As the ages pass, the supply of radioactive elements that keeps Earth's interior warm will dwindle. The core will cool by imperceptible degrees, and the mantle's great churning currents will lose their strength. Volcanism will still exist, but eruptions will become rarer and weaker, their plumes releasing less steam into the air. This subtle change will have consequences far beyond the volcanoes themselves. For billions of years, volcanic outgassing has replenished Earth's atmosphere and hydrosphere, returning water locked in the mantle back to the surface. It is part of the deep water cycle, a loop that connects the hidden interior of the planet with the sky and the sea. As the interior quiets, that loop will slow, and less water will be added to the surface reservoirs that evaporation and escape slowly erode. Earth will begin to leak water into space faster than it receives it back. The balance will tilt, so slightly at first that it will pass unnoticed, but the imbalance will grow with time. Tectonic forces will fade too. The vast plates that drift across the surface, colliding and consuming one another, are driven by the same internal heat that fuels volcanism. As the mantle's circulation weakens, subduction zones will slow their relentless pull. The conveyor belt that drags water-rich crust downward and lifts magma upward will begin to stall. The recycling of water from surface to interior and back again will lose its efficiency. Oceans that once seemed eternal will no longer be replenished at the same pace, and the global reservoir will shrink by degrees too small for any living thing to notice. Even the atmosphere will conspire in this quiet transformation. Over geological timescales, the carbon dioxide that warms the planet will be steadily drawn from the air by chemical weathering. As mountains rise and erode, silicate minerals will react with rainwater, binding carbon and storing it in stone. This reaction cools the climate and, more subtly, locks away small amounts of water in mineral structures. Over millions of years, this gradual sequestration will trap moisture deep within the crust, hiding it from the hydrological cycle. Rivers will carry sediments and dissolved minerals to the sea, where they will settle and bury water within the growing layers of oceanic crust. Continents themselves will shift in ways that reshape the fate of water. As plates slow and rearrange, ocean basins will deepen. Some shorelines will retreat not because water has vanished, but because the crust beneath the seas has subsided, creating vast depressions where water will pool more thinly. Elsewhere, continents may converge, closing off seaways and trapping portions of the ocean in inland basins. These isolated seas will evaporate more quickly, leaving behind salt flats and mineral crusts where waves once rolled. The changes to the planet's surface will be subtle but cumulative. Over millions of years, rainfall will become more uneven. Regions that were once lush with rivers and wetlands will slip into aridity, while deserts will expand and merge, lakes will shrink, rivers will dwindle, and groundwater will retreat deeper underground. With less water cycling through the air, global precipitation patterns will shift. Some areas will experience longer droughts and shorter rainy seasons. Even the chemistry of the oceans will evolve. As evaporation slowly exceeds replenishment, salinity will rise, altering ecosystems and driving marine life toward extinction or adaptation. The biosphere will feel the consequences long before the last ocean is gone. Plants and animals that depend on abundant rainfall will be pushed toward the poles or into shrinking pockets of habitable land. Wetlands will vanish, forests will thin, and grasslands will give way to desert scrub. As fresh water becomes scarcer, rivers will carve shallower valleys, and deltas that once teemed with life will crumble into dust. The cycle of water that has sustained every living thing will still function, but it will be weaker, more fragile, and less capable of supporting complexity. All of these changes will unfold over spans of time so long that they defy ordinary understanding. They will not happen in centuries or even in millions of years, but across the deep clockwork of geological ages. The oceans will still stretch from horizon to horizon for much of this time. Rain will still fall, and snow will still crown the mountains. Yet with each passing eon, the balance will shift, and the great planetary reservoir will drain ever so slowly away. The end will not come as a sudden calamity, but as a long and patient fading. Earth will not lose its water in a single moment. It will simply grow drier with each geological heartbeat, its rivers thinner, its lakes shallower, its oceans more saline and more distant from the land. The decline will be almost invisible, measured not in human history but in planetary memory. And by the time the final chapter approaches, when the last seas begin to lift skyward and vanish into space, the long, slow retreat will already have written most of the story. When we picture Earth's water, our minds drift first to the familiar, the rolling waves of the sea, the glittering surfaces of rivers and lakes, the clouds drifting above them. Yet what we see is only a thin skin on the planet's surface. A far larger, quieter story unfolds below our feet, hidden beneath stone, sealed beneath ice, stored in places so remote and so strange that they might as well belong to another world. Most of this water is never touched by sunlight or stirred by wind. It lies buried in darkness, shaping the planet from within. Just beneath the ground, beyond the reach of roots and rain, lies a vast and intricate web of hidden reservoirs. These are the aquifers, ancient vaults of water held within porous rock and sand. They are not underground lakes in the way we might imagine. Instead, they are networks of tiny spaces between grains of sediment and fractures in bedrock, each one holding water that seeped slowly downward, sometimes over thousands or even millions of years. Some aquifers are shallow and regularly replenished by rainfall. Others are sealed deep below the surface, untouched since the days when ice sheets last blanketed the continents. In many parts of the world, these buried stores stretch for thousands of kilometers beneath the land. They hold more fresh water than all of Earth's rivers combined and sustain vast ecosystems without ever breaking the surface. Forests draw on them through the soil. Springs emerge from their edges to feed streams. Cities drill into them to supply drinking water to millions. Yet these underground reservoirs are more than just a resource. Locked inside them is a chemical record of the past, traces of volcanic eruptions, ancient rainfall patterns, even the imprint of climates that vanished long before humans appeared. In their stillness, they hold the memory of worlds long gone. Deeper still, water hides in stranger places. Beneath the immense ice sheets of Antarctica and Greenland, far below the frozen surface, lie lakes that have been sealed off from the atmosphere for millions of years. These are the subglacial lakes, buried under kilometers of ancient ice, their existence unknown until radar instruments peered beneath the frozen crust. They are cut off from sunlight, isolated from the weather above, and yet they remain liquid. The crushing weight of the ice above, combined with heat rising from the planet's interior, keeps them from freezing solid. Lake Vostok is among the most remarkable of these hidden worlds. Buried beneath nearly 4 kilometers of Antarctic ice, it has been isolated from the surface for at least 15 million years. The water inside has never seen the open sky, yet scientists believe it may harbor life adapted to the intense pressure, the darkness, and the chemical energy from minerals beneath the lake bed. Other subglacial lakes, some only a few kilometers wide and others stretching for hundreds, lie scattered beneath the ice sheet like forgotten seas. Together, they form a secret aquatic landscape, one that exists entirely out of sight. Even the massive glaciers themselves conceal water within and beneath them. As ice moves slowly toward the sea, friction against the bedrock below generates heat, melting some of the ice at its base. This thin film of water acts as a lubricant, shaping the speed and direction of the glacier's flow. It also gathers into channels and pockets, forming subglacial rivers that carve their way through stone and transport sediments toward the ocean. Though hidden, this water plays a crucial role in the behavior of ice sheets and in the rise and fall of sea levels. Far below even these icy realms, beyond the reach of drills and sensors, lies another kind of water entirely. Trapped deep within minerals, bound at the molecular level, water exists as part of the very fabric of the planet. It does not flow or freeze. It does not fill lakes or seep through soil. It is locked inside crystals, woven into the structure of the rock itself. Over geological timescales, this water can move as tectonic plates descend into the mantle and later return to the surface through volcanic eruptions. It is a cycle so slow and so deep that it operates on the rhythm of continents rather than storms. And still, the story may go deeper. Some scientists suspect that pockets of superheated water circulate far below the crust, hidden within the planet's mantle, rising and falling in convection currents we can barely imagine. Others propose that water might exist near the boundary between mantle and core, influencing how heat moves through the interior and how the magnetic field behaves. These possibilities remain uncertain, but they hint at a truth that is becoming clearer with every discovery. Water is not confined to the surface world we know. From the gentle seep of an underground spring to the dark, silent depths beneath miles of ice, Earth is saturated with hidden water. It shapes landscapes from below, fuels geological forces, and preserves fragments of the planet's history that would otherwise be lost. What we see on the surface is only the beginning. Beneath the crust and beneath the glaciers, water continues its quiet work, binding together the deep interior and the living world above, a reminder that even in darkness and stillness, Earth is never truly dry. Water has never stood still. Since the first drops pooled on the surface of a cooling Earth, it has been on a journey that never ends. It evaporates and falls, freezes and flows, hides deep underground and returns again to the light. It is patient, unhurried, and tireless, shaping landscapes and fueling life while carrying the memory of everything the planet has ever been. This continuous motion is not just a process, but a kind of heartbeat, one that links the skies to the seas and the deep interior to the air above our heads. It begins with the warmth of the sun, the same force that has driven the cycle for billions of years. When sunlight touches the surface of the oceans, rivers, and lakes, it gives water molecules enough energy to break free and rise into the air. This invisible ascent, called evaporation, sends water drifting upward as vapor, joining the swirling currents of the atmosphere. There it cools and condenses into clouds, vast gatherings of tiny droplets carried by winds across continents and seas. Eventually, the journey turns downward again. Clouds grow heavy, and water falls back to earth as rain, snow, sleet, or hail. Each drop that returns begins a new story. Some fall directly into rivers or oceans, closing the loop almost immediately. Others land on soil and seep downward, nourishing roots and filtering through layers of rock to recharge underground aquifers. Still others collect into streams that merge into rivers, carving valleys and sculpting canyons as they make their way toward the sea. Over centuries, rivers reshape entire continents, moving sediment from mountains to deltas and leaving behind fertile plains that sustain forests, grasslands, and civilizations. But the water's journey does not stop at the surface. Much of it continues deeper, pulled by gravity into cracks and fissures in the crust. Some remains there for thousands of years, locked in hidden aquifers, Some travels farther still, drawn downward at the edges of tectonic plates. Where one plate sinks beneath another, fragments of oceanic crust, soaked with water, are carried into the deep mantle. There, under immense heat and pressure, the water becomes part of the rock itself, bound within minerals and hidden away for millions or even billions of years. Yet, even in the depths, water's story does not end. The same forces that pull it downward eventually push it back toward the surface. Heat within the planet melts rock, forming magma that rises slowly upward. Carried with it is some of the water that was buried long ago. When volcanoes erupt, that water is released as steam and gas, returning once more to the atmosphere. What began as rain can end its journey as vapor rising from the heart of the earth. This deep connection between the surface and the interior is more than a geological curiosity. It is part of the reason Earth's climate remains stable over immense spans of time. Water vapor in the atmosphere helps trap heat, moderating temperatures and keeping the planet warm enough to sustain liquid oceans. Rainfall distributes that heat around the globe, carrying warmth from the equator toward the poles. Oceans, in turn, circulate water and energy through powerful currents, influencing weather patterns and regulating climate. Without this constant movement, Earth's surface would swing between extremes, and the conditions for life would be far less stable. The water cycle also acts as a planet-wide recycling system, one that links rocks, air, and living things. Rain wears away mountains, dissolving minerals and carrying them to the sea, where they feed marine ecosystems and form new layers of sediment. Subduction drags those sediments deep into the mantle, where they melt and mix with the planet's interior. Volcanic eruptions then return some of that material to the surface, creating new land and replenishing the atmosphere with gases and water vapor. It is a slow, circular exchange that has repeated for billions of years, constantly renewing the surface of the Earth. Even the smallest parts of this cycle have far-reaching effects. The gentle fall of rain can change the chemistry of the atmosphere. The steady flow of rivers can shift the balance of nutrients in the ocean. The release of water from a distant volcanic eruption can alter the climate across an entire hemisphere. Each motion, no matter how subtle, is part of a greater rhythm, one that connects sky and sea, rock and cloud, heat and life. And it never truly stops. Through ice ages and greenhouse epochs, through the rise and fall of continents, water continues its endless circuit. It links the surface world with the planet's deepest layers, binding Earth into a single, dynamic system. The drops that rise into the sky today may one day fall as rain on a distant continent, seep into the crust, and emerge centuries later from a volcanic vent. In this way, water binds the passage of time itself, moving steadily through cycles that outlast mountains, oceans, and species alike. From the clouds above to the mantle below, from the rivers that carve the land to the steam that escapes from volcanic vents, water is always in motion. It is the invisible thread, stitching together every part of the planet, the quiet engine that renews, reshapes, and sustains it. And as long as it moves, the story of Earth will keep unfolding, written not in ink or stone, but in the endless flow of water through the world. When we look up at the night sky, it is easy to believe that Earth is ordinary. Planets circle countless stars, and many of them, we now know, hold water in some form. Yet the deeper scientists search, the clearer it becomes that Earth is not typical at all. Its oceans, its atmosphere, and the delicate balance that allows water to exist on its surface are rare and precious. And nowhere is this lesson clearer than when we look beyond our own planet to the worlds that orbit beside us and far beyond. In the cold outer reaches of our solar system, Far past Mars and the asteroid belt, two small worlds hide a remarkable secret beneath their icy crusts. Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, are frozen on the outside, their surfaces locked beneath shells of solid ice. At first glance, they seem lifeless, barren, and inhospitable. But below those frozen shells lies something extraordinary: vast oceans of liquid water. Europa's ocean is thought to be immense, containing more water than all of Earth's oceans combined. It is kept from freezing not by sunlight, which is weak and distant so far from the sun, but by the powerful gravitational pull of Jupiter. As Europa orbits, Jupiter's gravity stretches and flexes the moon, generating internal heat that keeps its buried ocean liquid. Beneath kilometers of ice, this hidden sea is in constant motion, its salty waters churning and circulating. Some scientists believe hydrothermal vents may exist on its seafloor, just as they do in Earth's deep oceans, potentially creating the conditions for life. Enceladus, smaller and colder, is no less intriguing. Its icy surface is fractured and crisscrossed with deep fissures, and from these cracks, plumes of water erupt into space. These geysers are not steam from the surface, but liquid water from a global ocean beneath the crust. The fact that water can escape into space tells scientists that this hidden sea is active and dynamic, and the plumes themselves contain more than water. They carry traces of organic molecules, the carbon-based ingredients that make up life, hinting that Enceladus might harbor something living beneath its frozen shell. These distant moons show that water is not confined to planets like Earth. It can exist in darkness, trapped under ice, sustained by forces other than sunlight. But they also reveal how precarious that water can be. On Europa and Enceladus, oceans are sealed away from the surface, locked beneath barriers of ice that isolate them from the wider universe. Any life that exists there would be cut off from sunlight, air, and the complex web of surface processes that shape life on Earth. These worlds remind us that while water is essential, it is not enough on its own. The right balance of energy, chemistry, and environment is just as crucial. The search for planets beyond our solar system has expanded this lesson even further. Astronomers have discovered thousands of exoplanets orbiting distant stars, and many of them show signs of having water. Some are water worlds, planets covered entirely by global oceans, with no continents at all. Others are icy giants with thick water layers trapped beneath deep atmospheres. At first, these discoveries were thrilling, suggesting that watery planets might be common. But the more we learn about them, the more we see how unusual Earth's balance is. A planet covered completely by water might sound ideal for life, but without continents, the carbon and mineral cycles that regulate climate could not function. With no land to erode, nutrients might never reach the oceans, and complex ecosystems might struggle to form. On planets where water is buried beneath thick layers of ice or gas, it may never interact with the surface at all, and on worlds too close to their stars, water quickly evaporates and is lost to space. Too far away, and it freezes solid. Earth sits in a narrow zone where conditions are just right. It is close enough to the sun to keep its water liquid, yet not so close that it boils away. Its gravity is strong enough to hold onto an atmosphere, but not so strong that the planet is smothered by it. It has continents to cycle minerals and oceans to distribute heat. It has plate tectonics to recycle water into the interior and volcanoes to release it back into the air. All of these factors together create the delicate equilibrium that makes Earth a living planet. Looking outward reminds us that water is not rare in the universe, but the conditions that keep it stable on a planetary surface are. Most worlds fall on one side of the line or the other: too cold, too hot, Too deep, too sealed, too volatile. Earth stands apart, not because it has water, but because it holds water in just the right way. From the hidden seas of Europa and Enceladus to the distant water worlds orbiting other stars, the cosmos shows us many versions of water's story, but none match the balance that exists here, on the small, blue world where liquid oceans have shaped continents, nurtured life, and written the story of a planet for billions of years. Earth's water is not just a feature of its landscape, it is a miracle of circumstance, one that, as far as we know, exists nowhere else quite the same. After the era of great bombardments, when asteroids the size of mountains collided with the young Earth and comets slammed into its surface with oceans locked inside them, a quieter form of delivery never stopped. It is happening now, this very moment, though it unfolds so gently that almost no one notices. Grain by grain, the cosmos still sprinkles material onto our planet. It is a soft rain of micrometeorites, no larger than sand, and often no heavier than a speck of dust. Each one carries traces of the same elements that built our oceans long ago. And though the amount they deliver each year is tiny, almost laughably so compared to the planet's vast seas, their patience is infinite. Over millions of years, this faint drizzle becomes measurable. The difference between this ongoing delivery and the violent events of the past could not be more striking. In the planet's early history, colossal impacts reshaped continents and released enough heat to boil oceans. Entire basins of water may have arrived in single events, sealed inside ancient comets or icy planetesimals that shattered on impact, but those days are long gone. The last of the truly cataclysmic impacts faded billions of years ago, leaving behind a world that had mostly gathered the water it would ever have. What remained was a slower, subtler process, one that has continued without pause since the first oceans formed. Micrometeorites are born from many different places. Some are the dusty remnants of asteroids shattered by collisions in the asteroid belt. Others come from comets that shed grains as they pass near the sun, their icy surfaces sublimating into gas. A few are ancient debris, leftovers from the original building blocks of the solar system, set adrift billions of years ago and only now falling toward Earth. Most are no bigger than a grain of sand, many weigh less than a fraction of a gram. Yet Earth's gravity draws them in all the same, sweeping them from the void and pulling them down through the thin shell of air that surrounds our planet. The journey through the atmosphere is often the end for these tiny travelers. Most burn away in streaks of light, creating the familiar sight of meteors across the night sky, but not all of them are destroyed. Some survive their descent, reaching the surface as microscopic grains that settle silently on mountaintops, deserts, ice sheets, and the floors of the oceans. Scientists have found them preserved in Antarctic snow, embedded in deep-sea sediments, and even resting unnoticed on the rooftops of cities. What makes these cosmic visitors so intriguing is what they carry. Many micrometeorites contain hydrated minerals, formed in the presence of water long before they ever encountered Earth. Others trap water molecules inside their crystalline structures, or carry compounds rich in hydrogen and oxygen, the two elements that combine to form water. And even when these particles vaporize during atmospheric entry, their hydrogen does not disappear. It reacts with oxygen in the air, producing new water molecules that eventually join Earth's hydrosphere. Individually, these contributions are almost unimaginably small. The total mass of water delivered by micrometeorites in a single year would barely register against the weight of the planet's oceans. But over geological timescales, the numbers begin to add up. Tens of thousands of tons of cosmic dust rain down every year. Stretch that over hundreds of millions of years, and the total becomes something scientists can measure, perhaps enough to fill entire inland seas. It is not enough to build oceans from scratch, but it is a steady supplement to the supply Earth already has. The slow accumulation of water from space is not unique to Earth. Every world that orbits the sun, from rocky planets to barren moons, is touched by this same drizzle. Even bodies without atmospheres receive it. On the moon, for example, some of the water molecules detected in surface rocks may have arrived this way, carried by micrometeorites, and fused into minerals upon impact. Mars, too, likely continues to receive small infusions of hydrogen and oxygen from interplanetary dust, some of which may contribute to the thin traces of water observed in its soil and atmosphere. Over deep time, these subtle processes can leave a noticeable mark, even on seemingly lifeless worlds. What makes this ongoing delivery remarkable is how quietly it bridges Earth's violent beginnings with its present. The ancient ocean-filling impacts of the early solar system and the gentle trickle of micrometeorites today are two ends of the same story. One was sudden and catastrophic, shaping entire planets in moments. The other is slow and constant, a patient continuation of the same cosmic process. Together, they form a continuum that has lasted for more than 4 billion years. Each grain that falls from space is a messenger from far beyond our skies. It may have formed in the icy crust of a comet orbiting beyond Neptune, or in the debris field of a shattered asteroid older than Earth itself. It may have traveled through the dark for millions of years before being captured by our planet's pull. And when it finally lands, it becomes part of Earth's surface, its air, and its water indistinguishable from the molecules that flow through rivers and cycle through clouds. The water in a glass you drink, the rain that falls on a forest, the ice locked inside a glacier may all contain atoms delivered by this cosmic drizzle. They are reminders that even in an era when the great collisions are long past, the universe is still shaping our world in quiet, invisible ways. The physics of this delivery is subtle, but its impact is real. And over the vastness of geological time, even the smallest grain from the stars can leave a measurable imprint on a planet like ours. In the farthest reaches of time, long after anything we know today has faded into memory, the story of water will approach its quiet ending. It will not end with an explosion or a sudden disappearance. It will not vanish overnight. Instead, it will unfold slowly in the measured rhythm of planetary change, shaped by the same star that once breathed life into the oceans in the first place. The sun that rises over Earth each morning is not eternal. Like all stars, it is evolving. Since its birth, it has been growing brighter, and in the distant future, it will shine far more fiercely than it does now. That change is almost imperceptible on human timescales, but over geological ages, it transforms everything. The warmth that once allowed water to pool and flow will, in time, become the force that drives it away. The first signs of this transformation will arrive so gradually that no creature alive will ever witness more than the faintest hints of it. Seas will still stretch beyond the horizon, waves will still crash against the shores, and clouds will still drift across the sky, but each passing eon will bring subtle shifts. Shorelines will begin to pull inward, low-lying coastlands will dry and harden into plains of salt and sand. Vast, deep oceans will slowly thin at their edges as evaporation outpaces rainfall. Centuries will become millennia, and millennia will become millions of years. In this long future, Earth will grow warmer. The air will hold more water vapor than it ever has before, and the cycle that once tied sky and sea together will begin to falter. Rivers will shrink into dusty channels, their flow too weak to reach the coasts. Lakes will fade into shallow basins, ringed by white crusts of salt that crunch under the weight of the wind. Vast continental interiors, once lush and green, will dry into barren plateaus. Eventually, even the oceans themselves will lose their vastness. They will retreat from the continents, breaking apart into isolated seas, clinging to the planet's lowest basins. Where once there were deep waters alive with currents and tides, there will be shallow, stagnant pools. The sound of waves will grow faint, replaced by the silence of wind over rock. The skies, too, will change. They will become brighter, heavier, and more stifling as water lingers longer as vapor. Great towers of cloud will form and disperse, but rain will fall less often, and when it does, it will evaporate before reaching the ground. Storms will be rare and fleeting, unable to sustain the cycle that has shaped Earth's landscapes for billions of years. As the centuries stretch into billions of years, the transformation will become unmistakable. The last inland seas will shrink into puddles that evaporate under an unrelenting sun. What remains of the oceans will lie trapped in deep depressions, hidden in shadows for a time before even those final pools vanish. The planet's surface will dry and crack, its once fertile soils turn to dust. Salt flats will spread across the empty basins where oceans once rolled. Their bright surfaces will glare under a brilliant sky, mirroring the harshness of the star overhead. Winds will sweep across the plains that were once seabeds, carving new landscapes from the remnants of the old. Ancient coastlines will remain as fossilized boundaries etched into the rock, ghostly markers of where the waters once reached. Life, if any remains by then, will cling desperately to the final refuges. Some may survive in subterranean pockets of moisture, deep below the reach of the burning atmosphere. Others may persist in the shadows of polar regions, where a trace of water lingers for a little while longer. But even these last survivors will face extinction as the heat intensifies and the world becomes too hostile for even the hardiest forms of life. In this distant future, Earth will be a world transformed. The landscapes will resemble those of its earliest days, long before oceans formed a planet of bare rock and vast desert plains, sculpted by wind and time. The skies will blaze a deep, unclouded blue, and the sun will hang heavier and brighter above the horizon, flooding the planet with light that no longer nurtures, only scorches. The memory of water will still be written into the world. Ancient river valleys will snake across the land, dry and lifeless. Seafloor ridges will stand exposed under the open sky. Fossilized coral reefs will lie in the heart of deserts, monuments to a vanished ocean. The minerals in the rocks will still bear the chemical fingerprints of water's long presence, and the sediments will hold the story of tides that once rose and fell. This is how the story of water will end, not with a sudden absence, but with a long retreat. The seas will not be stolen in an instant. They will slowly, almost gently, slip away, leaving behind salt plains, stone basins, and a silence deeper than any storm. Where waves once thundered against the shore, there will be nothing but wind whispering over rock. Where rain once nourished forests, there will be nothing but sunlight falling on dust. And beneath that relentless light, Earth will stand as it did at the very beginning, a world stripped bare, its oceans gone, its surface etched with the memory of what once was. The chapter that began with the first drop of rain will close with the last trace of water vanishing into the air, leaving behind a planet shaped, sustained, and finally surrendered by the force that once defined it. Every drop of water you have ever tasted, every tear that has ever fallen, Every breath of moisture in the air around you shares a single, astonishing truth. It is far older than Earth itself. Long before continents rose, before oceans gathered, before even the sun began to shine, the water that now flows through your veins was already ancient. It was forged in the quiet heart of the cosmos, in a universe that was still young and raw. To understand this story, we must go back farther than the birth of Earth, farther even than the birth of the solar system. Around 13.5 billion years ago, the universe itself was born in the event we call the Big Bang. In that moment, space and time began to expand, and the first elements came into being. Among them was hydrogen, the simplest and most abundant element in existence. Every atom of hydrogen in the water you drink today was created in those first moments of cosmic existence when the universe was no more than a roiling sea of particles and light. Hydrogen alone, however, is not water. For that, it needed to find a partner, oxygen. But oxygen was not part of the universe's first recipe. It had to be built in the fiery hearts of stars. When the first stars ignited, they began fusing lighter elements into heavier ones, creating carbon, nitrogen, and eventually oxygen. When those early stars reached the ends of their lives, they exploded as supernovae, scattering the elements they had forged into the cold darkness of space. It was in this way, through cycles of birth and death on a cosmic scale, that the universe was seeded with the ingredients for water. Hydrogen and oxygen met in the vastness of interstellar space, often in regions known as molecular clouds, immense, cold nurseries where new stars and planets are born. In these clouds, the two elements combined to form water molecules, which clung to grains of dust and froze into tiny crystals. These particles drifted through space for millions of years, gathering in great clouds that slowly collapsed under gravity's pull. One such cloud, about 4.5 billion years ago, gave rise to our solar system. Inside that collapsing cloud, water was already present. It coated the dust and rock that swirled around the newborn sun. As planets began to form, those water-rich grains were swept up into larger bodies, becoming part of asteroids, comets, and eventually planets themselves. The water that fills our oceans and flows in our rivers today likely originated in those icy grains, which had themselves formed long before the sun ever existed. This is why scientists believe that much of Earth's water is older than Earth. The hydrogen atoms in every molecule are relics of the Big Bang. The oxygen atoms were forged in ancient stars that lived and died billions of years before our planet was born. And the molecules themselves, likely assembled in the cold darkness of space, drifting for eons before becoming part of the rocks and ices that built our world. This deep cosmic ancestry extends beyond the oceans and into you. More than half of your body is water. It carries oxygen to your cells, cushions your organs, and allows every chemical reaction that sustains life to take place. That means the water flowing through your veins is not just old, it is timeless. It was born in the heart of the universe's first fire and shaped by the death of ancient suns. Long before there was a planet for you to stand on, before there was a sun to warm your face, that water was already here, waiting. It is a strange thought, but a profound one. The glass of water in your hand is a relic of events so ancient that the human mind struggles to grasp their scale. It contains atoms that once drifted between the stars, particles that may have passed through countless cosmic journeys before becoming part of you. The molecules that allow you to blink, breathe, and dream are fragments of the universe's oldest story, still flowing and cycling through new forms billions of years after they first came into being. Even as Earth changes, even as oceans rise and fall, The water itself endures. It migrates from the sea to the sky, from the soil to the clouds, from the deep mantle to the surface. It becomes rain, ice, blood, and vapor. It is swallowed and exhaled, frozen and melted, buried and released. Yet through all of those transformations, it remains what it has always been, a link to the earliest chapters of existence itself. The water in your body does not simply connect you to Earth, it connects you to the Big Bang, to the first stars, to the long, patient unfolding of cosmic time. It is a memory older than worlds, older than suns, older than life. And with every heartbeat, that memory moves through you, whispering a story that began long before the first planet formed and will continue long after the last one fades. Every story life has ever written began with water. It is not just a background detail or a setting in which life unfolded. It is the ink itself, the thread that ties together every chapter, from the first spark of chemistry on a young Earth to the rise of beings who can look back and ask how it all began. To understand life's story, we must follow the journey of water, because every milestone, every turning point, was shaped by its presence. Long before the first cell existed, water was already at work. In the deep cracks of the ocean floor, where heat and minerals met the chill of seawater, chemistry began to organize itself. Molecules that once drifted aimlessly collided and linked together, forming more complex structures. Over countless ages, these reactions built the foundations of life. Without water's ability to dissolve, transport, and bring molecules into contact, this process might never have begun. In water's embrace, matter learned to replicate and evolve. When life finally took its first breaths, it did so beneath the surface of the sea. The earliest organisms floated in a world of liquid, drawing nutrients from it, shielding themselves within it, and using it to move and grow. Oceans provided not only stability, but also protection. They buffered temperature, absorbed harmful radiation, and offered an almost endless space for life to experiment. In that sheltering vastness, single cells learned to cooperate, forming colonies that grew more complex with time. Over hundreds of millions of years, water continued to shape the course of evolution. Early life relied on it not only as a home but also as a chemical partner. It carried oxygen and carbon dioxide, allowed cells to build energy, and acted as the medium through which signals passed. Even as organisms diversified, branching into countless forms, they all remained bound by this dependence. Every cell, no matter how simple or complex, remained a tiny droplet of ocean enclosed within a membrane. Then came one of life's most daring moves, the conquest of land. Around 400 million years ago, plants began to leave the water's edge, pushing onto damp shorelines and shallow mudflats. But they did not abandon their connection to water. Instead, they adapted to bring it with them. Roots evolved to draw it from the ground, stems to transport it upward, leaves to regulate its loss. Even their reproductive cycles, at first, relied on water to carry sperm to egg. Forests that now stretch across continents are, in essence, towering networks designed to capture and circulate water. Animals followed. Fish, shaped and sustained by water, gave rise to amphibians, creatures that could move between two worlds. Their skins remained moist. Their eggs still required water to develop. Over time, reptiles and mammals evolved ways to conserve water more carefully, sealing themselves against the air, yet even they carried their watery origins within. Blood, sweat, tears all are echoes of the ocean's life once called home. Water's influence did not stop at biology. It sculpted the very stage on which evolution unfolded. Rivers carved valleys that became migration routes. Lakes formed isolated environments where species diverged and diversified. Ice sheets advanced and retreated, forcing life to adapt to shifting climates and new landscapes. Even mass extinctions were tied to water's rhythms, triggered by changes in sea level, temperature, and chemistry that reshaped entire ecosystems. As evolution marched forward, water remained at the center of every transformation. It fueled the rise of vertebrates, whose circulatory systems evolved to move water rich blood. It nourished the first flowering plants, whose intricate structures allowed them to regulate water with exquisite precision. It sustained the great forests that oxygenated the atmosphere, paving the way for complex animal life. And it supported the vast web of marine ecosystems that remain the foundation of Earth's biodiversity today. Even the emergence of humans was shaped by water. Our ancestors followed rivers as they spread across continents. They built their first settlements beside lakes and deltas where fresh water supported crops and animals. Civilizations rose where water was plentiful and collapsed when it vanished. Entire cultures built myths, rituals, and philosophies around its cycles, understanding on some deep level that their survival was tied to its flow. Inside you, water still carries this ancient legacy. It makes up most of your body, flows through your veins, and fills every cell. It delivers nutrients, removes waste, and regulates temperature, performing the same essential roles it did in the first living things. Every heartbeat is a ripple of that same force that once surged through primeval seas. Life has never existed without water, and it likely never will. Across billions of years, through extinctions and explosions of diversity, it has been the constant companion of evolution, guiding its direction and setting its pace. It is not simply a requirement for life, it is life's medium, its catalyst, and its memory. From the smallest bacterium to the most complex mind, every living thing is, at its core, a pattern written in water. And as long as water flows across this planet, the story of life will continue to unfold. From the first gardens scratched beside a stream to the sleepless shimmer of modern skylines, water has been the quiet partner of everything people build. It decides where a town takes root, how a city grows, and whether a harvest will stand or fail. It moves beneath streets and fields in unseen channels, keeping the lights on, the food growing, and the air clean enough to breathe. Long before walls and roads, people followed river bends the way birds follow coastlines. A bend in the water meant fish in the shallows, reeds for thatch, and soft soil that welcomed seeds. Later, when farming began, water shaped the calendar. Floods laid down silt, then receded, and farmers learned to guide the leftover trickles into ditches and furrows. Canals, wells, and terraces widened the reach of a single stream. With each small advance, more mouths could be fed, and scattered camps began to hold fast. Rivers became roads, boats carried salt, grain, pottery, and stories. Harbors turned into marketplaces where distant languages mixed with the cries of gulls. As ships grew stronger, coasts stitched worlds together. A port that could load and water a fleet became a center of gravity, pulling craftsmen, traders, and ideas to its docks. Water did not only grow food, it moved wealth. Inside the city, water does quieter work. It arrives at the edge of a reservoir, settles in the dark of a settling basin, and then passes through membranes and carbon and light. Pumps lift it through miles of pipe, valves hum open, meters spin. At the tap, it looks simple, but behind that clear stream stands an orchestra of treatment and pressure that must play without a missed note. Outflow matters as much as inflow. Sewers gather what the city has used and carry it to plants where it is cleaned, tested, and return to a river that must stay alive. Public health lives in those pipes. In crowded neighborhoods, clean water and sanitation are the difference between a routine day and an outbreak. A clinic needs sterile water for instruments. A bakery needs hot water for dough and for hands. A school needs fountains and sinks that work every single hour. When the system stumbles, illness does not wait. Industry rests on water in thousands of quiet ways. A forge needs quenching, a mill needs washing, a refinery needs process water that leaves no mineral trace behind. Semiconductor lines demand water that has been stripped of almost every ion and speck, polished until it is nearly a blank canvas. Food processing plants rinse and blanch in steam. Breweries coax sugars into something new. Textile lines dye and set color that will not run. None of it works without reliable flow, steady temperature, and careful cleaning at the end. Energy depends on water with a grip that is easy to miss. Hydropower turns falling water into motion. Thermal plants, whether they burn fuel or split atoms, must carry heat away from their cores, and that heat goes into river water that circles through towers and returns cooler and safe. Even solar fields and wind factories lean on water for cleaning, for concrete, for steel, for the quiet logistics of building and keeping them running. When a drought lowers a reservoir beyond intake height, power can falter even under a cloudless sky. Modern life adds new kinds of thirst. Data centers keep the world's conversations and records within reach, but servers run hot. Many facilities depend on loops of chilled water to keep circuits in their narrow band of comfort. Warehouses mist the air to keep dust from sensitive stock. District cooling moves cold water under downtowns, so offices do not each need their own clattering units. A silent lattice of pipes makes the hum of a city sound effortless. Far from the city, fields still pull the largest share. Canals and drip lines turn arid valleys green. Pivot arms sweep circles across the land like slow clock hands. The yield of a season can hinge on snowpack held in the high country, released as melt into rivers at just the right pace. Reservoirs smooth the rough edges of dry years, and groundwater stands ready when the surface falls short, but aquifers do not refill on command. When pumping outruns the slow gift of recharge, wells drop and soils settle. Transport follows water too. Barges push grain and ore along inland routes that cost a fraction of rail. Locks and dams keep channels deep enough for heavy hulls. Coastal shipping hops from port to port through straits where currents set the schedule. Even in the air, water plays a part. As de-icing plants and fire suppression systems stand ready for days when engines and wings need help. Emergency systems lean on water as their first tool. Firefighters pull from hydrants and cisterns. Helicopters dip buckets into lakes. Hospitals hold reserves behind locked doors for the hours when mains fail. When a storm snaps lines and a city goes dark, the race is not only to fix wires but to keep pumps turning so pressure does not fall. The chain is only as strong as its hidden links. Intake screens must stay clear of algae blooms. Treatment plants need power and chemicals and trained hands. Pipes must be mapped, maintained, and replaced before small leaks become sinkholes. Metering and pricing must keep pace with reality so that waste does not eat the future. Farmers need schedules that share rivers fairly across valleys and borders. Builders must keep roofs and streets that can catch a hard rain without sending it into basements and rails. When water grows scarce, the weakness of each link shows at once. Fields go from green to gray. Barges ride lower and scrape on bars. Factories slow lines to meet discharge permits. Power stations derate to protect fish and keep temperatures safe. Neighborhoods line up at tankers parked under a hot sun. The city's pulse becomes uneven. In a few days, every part of the system feels the tug, yet the same network can carry answers. Pipes can lose less if sensors find leaks early. Crops can drink less if roots see steady drips instead of floods. Cooling can return to closed loops that waste less heat and draw fewer gallons. Streets can send storms into gardens and cisterns instead of gutters. Wastewater can be polished into water pure enough to drink again, a circle closed without a seam. Civilization does not ride on water in theory. It rides on it in pumps and gaskets, in welds and gauges, in the steady thrum of stations that run through the night. Every morning coffee, every charged phone, every loaf on a shelf carries the trace of that hidden labor. Keep it flowing, and a city hums. Let it falter, and the hum stops, one quiet valve at a time. For centuries, humans have traced rivers back to their sources, followed rain clouds across the sky, and drilled deep into the ground to find the water hidden below. Yet, for all we have learned about this precious substance, one question still lingers unanswered at the very heart of science. Where did it all come from? It seems simple at first glance. Water is everywhere, from the oceans that cradle life to the clouds that drift above us. But the deeper scientists look into its origin, the more complicated the story becomes. The mystery has not vanished with time. If anything, it has grown larger, stretching backward billions of years into an era when the planet itself was still forming. At first, the explanation seemed obvious. Water must have been delivered to Earth from space. The early solar system was chaotic, a vast, swirling disk of dust, gas, and frozen debris colliding and merging under gravity's pull. In this violent environment, countless icy bodies from the outer regions would have been flung inward, striking the newborn Earth and releasing their water upon impact. For a long time, this idea felt like a satisfying solution. It explained how a planet that formed in a hot, dry region near the sun could still end up covered by oceans. Each asteroid, each icy fragment that collided with Earth, would have brought a small but meaningful gift of water, and over millions of years, those gifts would have accumulated into seas. But as technology improved and scientists gained the tools to test these ideas, cracks began to appear in the simple story. By examining the chemical fingerprints of water from different sources, researchers discovered that the water found in most comets did not match the water in Earth's oceans. The ratio of hydrogen isotopes, a kind of molecular signature, was often different, suggesting that comets were not the primary source after all. Attention shifted to another group of objects, carbonaceous chondrites, water-rich asteroids from the outer asteroid belt. Their isotopic composition matched Earth's water far more closely, hinting that these primitive rocks, not icy comets, may have delivered much of the water we see today. Yet even that answer is incomplete. If asteroid impacts were the main source of Earth's water, then why does evidence show that liquid water existed so early, possibly before the bombardment had finished? How could ancient zircon crystals, formed within the planet's crust, contain signs of water long before these collisions had time to deliver enough of it? The timing does not fully align, and the puzzle deepens the more closely we examine it. A competing theory suggests that water might not have arrived from the outside at all. Instead, it could have formed deep within the planet itself. Hydrogen, one of the most common elements in the universe, was abundant in the early solar system. Some of it became trapped in Earth's mantle as the planet coalesced. There, under immense pressure, it combined with oxygen from silicate minerals to form water molecules. Volcanic eruptions would have carried that water to the surface as steam, which eventually condensed into rain and filled the basins that became oceans. This internal origin theory explains how water might have appeared before the heavy bombardment ended, and why so much remains locked deep within Earth's interior to this day. But even this idea leaves questions unanswered. If water formed within Earth, how much of it did so? Was it enough to account for the vast volume of the oceans, or did the planet still require a significant contribution from space? And if both mechanisms played a role, in what proportions did they shape the final result? These questions remain at the center of ongoing debates in planetary science. There is also the possibility that we are overlooking an entirely different source. Some scientists propose that Earth's building blocks, the planetesimals that merged to form it, may have contained water from the very beginning. If true, water was never truly delivered or created here. It was present from the start, locked inside the rocks that became Earth itself. Others wonder whether water could have formed through chemical reactions in the early atmosphere, or whether it was absorbed from the nebula of gas that surrounded the young sun. Each possibility changes the timeline and the narrative, and each carries implications for how common water might be on other planets. The mystery is far from academic. Understanding where Earth's water came from could help answer one of humanity's most profound questions. How common is life in the universe? If water is rare, the result of a fragile chain of unlikely events, then perhaps living worlds like ours are equally rare. If, on the other hand, water is a natural outcome of planetary formation, then oceans, clouds, and rivers may be far more common than we imagine. For now, the truth remains just out of reach. Scientists continue to collect clues, from meteorites and mantle samples to the atmospheres of distant exoplanets. With every discovery, the story grows richer and more complex. The ocean beneath our feet is not just a simple reservoir, it is a cosmic puzzle pieced together from collisions, reactions, and processes that began long before Earth even existed. And though we may never know the precise balance of those origins, the search itself continues to teach us about our place in the universe and about the extraordinary journey that brought water and life to this world. For most of the universe's history, water was nothing more than a simple chemical bond scattered through the vast dark between stars. Hydrogen, born in the furnace of the Big Bang, met oxygen forged in the hearts of dying suns, and together they created one of nature's most extraordinary molecules. Yet for billions of years, those molecules drifted in clouds of dust and gas, frozen to grains of rock or locked within ancient asteroids, waiting for a home they might one day transform. They were patient, and eventually that home appeared. 4.5 billion years ago, a young planet began to take shape around a newly formed star. It was a place that, by all logic, should never have known water at all. It formed too close to the sun, where heat should have kept every drop in gas form. It was born from collisions and chaos, from molten rock and violent impacts, its surface too hot for oceans, and its skies too thin to hold rain. Everything about Earth's beginnings suggested a future of dryness and silence, and yet, something remarkable happened. Water arrived. It came not in a single flood, but in fragments. Icy planetesimals from the outer solar system rained down upon the surface, delivering their hidden cargo in fiery collisions. Water was trapped deep within the planet itself, rising slowly from the mantle as volcanic steam. It condensed in the cooling skies, fell as endless rain, and carved the first basins and valleys. Drop by drop, lake by lake, the impossible began to take shape. Oceans spread across the crust, clouds gathered in the air, and rivers traced paths toward the sea. What began as scattered molecules drifting through interstellar space became something far more profound, a planetary ocean. And once water took hold, it changed everything. It cooled the surface and softened the crust. It shaped mountains and carved canyons. It dissolved minerals and carried them across continents, laying the groundwork for the chemistry of life. It filled the air with moisture, softened the climate, and made the planet's surface a place where complexity could grow. Life itself rose from this watery foundation. In the deep, dark places of the early oceans, simple molecules assembled into self-replicating forms. From those humble beginnings, everything followed. Bacteria transformed the atmosphere, plants conquered the land, and animals filled every corner of sea and sky. Even the continents, pushed and pulled by the slow motion of tectonic plates, were shaped by water's gentle persistence. Over eons, it built landscapes, sculpted ecosystems, and sustained evolution's endless experiments. Yet water's story is not just about the distant past. It is written into every heartbeat of the present. It cycles endlessly between sea and sky, evaporating, condensing, falling as rain, and returning once more. It flows beneath our feet, locked in aquifers and hidden lakes. It moves through every living thing, coursing through roots and veins, powering the cells that make life possible. Every breath you take carries traces of water exhaled by countless organisms before you. Every sip you drink is built from molecules older than the planet itself. It is easy to forget how unlikely all of this is. Earth's water was never guaranteed. It did not have to be delivered by distant asteroids. It did not have to rise from the mantle or fall as rain. It did not have to persist through cosmic bombardments, global freezes, and mass extinctions. It could have been lost to space, boiled away under the young sun, or locked forever in stone. Yet against every expectation, it stayed. And because it stayed, so did everything that followed. Today, more than 70% of Earth's surface is covered by water, a vast, shimmering ocean under an endless sky. But the story behind that ocean reaches far beyond our planet. It stretches back to the first moments of the cosmos, to the forging of elements in ancient stars, and the slow assembly of planets from dust and gas. Every droplet carries that cosmic memory. Every wave that breaks on a shore is part of a tale billions of years in the making. And so, when you touch water when it falls as rain on your skin, when you hold a glass of it in your hand, or when you gaze out across the sea, you are touching the universe's oldest story. It is the story of how hydrogen and oxygen found one another, how a barren world became blue, and how life emerged where none should have existed. It is the story of how a lifeless rock was transformed into a living world. Water is more than a substance. It is the thread that connects stars to planets, chemistry to biology, and the past to everything still to come. It is the reason Earth is not just a planet, but a home. And every drop, whether in the deepest trench or the smallest tear, is a reminder of the miracle that turned an impossible world into the only one like it we know.